Okay, good morning, everyone. Just while everyone's logging on, a quick sound check. Can I get a nod if you can hear me? Great. Okay, well, welcome everyone to day 2 of the roundtable for the Burrow Creek project. Just a couple of preliminary matters before we get stuck into our theme day for today, which is surface water and groundwater. We have delayed our site visit, which we were hoping to conduct earlier this week to next week because of reports of rising river levels, and it wasn't clear that we'd be able to get access to enough of the project sites to make it worthwhile driving all the way up there. So what our current plan is to go, really hoping that Monday isn't a full day and that we could leave on Monday afternoon and do the site visit on Tuesday. We are very keen to do the site visit before the roundtable concludes in case there are questions that we have for the parties that arise out of the site visit, but we remain subject to the whims of the weather and the floods. So we'll see how we go, but that's our current plan. Mr. Forrester, I thought it would just be worth going through the kind of so-called homework list that we developed on last Friday, just to make sure that we've got the same list as what you've got. And we discussed on Friday a number of matters to be addressed in either a technical note or in closing submissions. The first item is more detail on how it's been demonstrated that the floodplain is in ecological decline. And, you know, just some detail around that. We'd be looking for some reference to the extent and location of dead and dying vegetation, shifts from aquatic to floodplain or floodplain to dryland communities, and shifts between different floodplain EVCs as sort of evidence of that ecological decline. The next matter was what underpins the assumption that the reversal of terrestrialisation will necessarily deliver better ecological outcomes. The next was, I think it was planned to be delivered by way of a technical note, but about the containment bank, including the nature and purpose of those spurs that we discussed on Friday, and any engineering constraints on having the riverside edge of the track defining. Sorry, it's about that centre line issue, what the extent of works being on the centre line rather than could it be pushed further away from the bank. We're going to have some questions for Dr. Treadwell about the containment bank today, but those we'll still need those kind of basic engineering kind of questions addressed as well. A list of the proposed works within 30 metres of the bank of the Murray, and just an explanation as to how that 30-metre distance from the bank of the Murray has been calculated, and whether consideration was given to whether any of those infrastructure items that are located within 30 metres could have been located outside that 30 metres. Quantification of the changes to the assessment of overall improvements to biodiversity in light of the war-cool effect. We mentioned on Friday that there was some sort of qualitative discussion of that, but there's not really a quantitative assessment of what the war-cool effect means in terms of the assessment overall improvements to biodiversity. And the last item on the list is why more native vegetation, why the extent of native vegetation loss proposed at Burrow at, I think it was 21.6 hectares, is quite a bit higher than that proposed in Nyah and Vinifera. That may be something that we can address through Mr. King, but we'll leave that to you. Are there any other preliminary matters that the parties wanted to raise before we get started with Mr. Foxley and Dr. Treadwell? Nope. Okay. Now, just in terms of how we run today, we understand Mr. Hoxley is only available today. We have relatively few questions for Mr. Hoxley. We have quite a lot of questions for Dr. Treadwell. So if this works for you, Mr. Forrester, we were proposing to hear the expert presentations first, and then we'll deal with questions of Mr. Hoxley first, so we can then concentrate on our questions of Dr. Treadwell. We would like Mr. Hoxley to remain online for the day in case, because, you know, there is an interaction between surface water and groundwater. So it may be that something comes up for Mr. Hoxley during the conversation with Dr. Treadwell, but we thought we'll get the questions from Mr. Hoxley out of the way first, if that works.
That seems perfectly suitable. The only thing that I would like to add to that in terms of the conduct of today relates to the manner in which those presentations are provided. And it was certainly the experience at the NIA and VMFRP Roundtable that it was both more productive of a fulsome and appropriate summary being provided, and more efficient for discussion, for questions, particularly from parties, to be held until after the presentations were complete.
Yes.
And the only thing by way of a preliminary matter that I'd like to raise is that I'd invite the committee to adopt the same approach here.
We will definitely adopt that approach. We have some specific questions in relation to specific slides, but we will go back to those and get the relevant expert to screen share at the appropriate time. But we would absolutely endorse that approach. I think it's a much more efficient approach. So we'll hand over to you.
Thank you, Member Carlisle. Consistent with the approach taken in ES Central and the NIA and VMFRP Roundtable, our experts have each prepared their written statements as well as presentations which have been tabled. I'll introduce them all now by way of their tabled document numbers so we can carry on through the both. Mr. Hoxley's statement is tabled document B12, and his presentation is tabled document B36. And Mr. Hoxley will speak to specialist assessment D, which is the exhibited groundwater specialist assessment, and to section 2 of the updated specialist assessments. Dr. Treadwell has prepared a written statement which is tabled document B13 and annexures in B13A, and a presentation which is tabled document B37. And Dr. Treadwell will speak to specialist assessment C, the surface water specialist assessment with the exhibited ER, and to section 3 of the updated specialist assessments. At the outset, and noting, as we've noted, and we noted on day one, that the methodologies adopted for the purposes of the specialist assessments are consistent with those adopted for previous projects and packages. We've asked Mr. Hoxley and Dr. Treadwell and all of the experts that we'll call to keep their focus very much on Burra Creek. And so the committee might notice in the course of the presentations that their focus in preparing those presentations has been perhaps less on the overall overarching questions of methodology and so on than has been the case in those previous packages, and particularly ES Central. But of course, we'll trust that the committee will raise with the experts those relevant matters which it considers are appropriately addressed. And they're certainly all addressed in writing in the witness statements and of course in the specialist assessment addendum documents. Similarly, and another statement relevant to all witnesses is that in large part, to the extent that witnesses have provided responses to submissions, those responses are in truth related to submissions in respect of not just the Burra Creek project, but all of the ER Central projects, or indeed all of the VMFRP projects. The responses are again contained in full in the written witness statements and addressed in the slides, but I expect the committee will understand that again the focus is on the Burra Creek project and contextualising those submissions and responses in that sense. And finally, I'll just note that these witnesses and all witnesses have made the relevant declarations in terms of their giving of evidence remotely in their written statements, so I won't take them to them orally. So at that point, I'll ask Mr. Hoxley to please come onto the screen and join us. And the committee will note Dr. Treadwell's here and sitting in the room, but I'll ask him to come online when it comes time to his presentation. And Mr. Hoxley, good morning.
Good morning, and can I check that you can hear me okay? Brilliant.
Thank you.
Thank you.
Now, Mr. Hoxley, your name is Greg Hoxley.
Yes.
And you're the author of a witness statement in respect of the Burra Creek project dated the 4th of August 2023.
Yes, I am.
And you were also the discipline lead for and the primary author of Specialist Assessment D to the exhibited environment report, and more recently for relevant parts of the Burra Creek addendum documents, including particularly section 2 of the updated specialist assessments.
Yes, I was.
Now, you're known to this committee and to the parties because of your previous evidence given in respect of EES Central and the VMFRP projects. Can I just confirm with you that your witness statement accurately sets out your qualifications and experience, as well as those other matters required by the planning panel's practice note in Annexure A and your CV at Annexure B?
Yes, it does.
Thank you. Now, Mr. Hoxley, at paragraph 5.3 of your statement, you identify that there was a transposition error in the surface water section of the updated specialist assessments, and in respect particularly of the salt loads attributed to the Burra Creek and VMFRP projects in the as exhibited environment report. As I understand it, your statement says that that's a transposition error, which doesn't fundamentally affect your groundwater assessment or the salt loads that you've assessed and assumed. Is that right?
Yes, that's correct.
And you've included in your statement a table at page 4. I might just share it on the screen. Table 1 of your witness statement, which deals with cumulative salt load effect. And as I understand it, you've updated this table to include, to fix the swapped numbers for the Burra Creek project here and the VMFRP project here. Is that right?
That's right.
All right. And have you had the opportunity to review Dr. Treadwell's witness statement and the table 1 that he has included in his witness statement?
Yes, I have.
All right. And Mr. Hoxley, you have noted in doing that in Dr. Treadwell's statement, he's included changes not just in respect of the transposition of those numbers directly, in the sense that he's fixed this number and this number, but in the sense that he has addressed those surface water implications in the sense of the total daily salt load and the cumulative increase which follows.
Yes, I have.
Okay. And for that purpose, and noting that your statement continues to use the numbers from the specialist assessments rather than the updated ones in Dr. Treadwell's statement, are you content for the committee to proceed on the basis of replacing your table 1 here with table 1 from Dr. Treadwell's witness statement?
Yes, I am. I tried to make the two tables the same, so that for convenience when comparing what I was saying about the groundwater outflow and then it being picked up in the surface water study, there would be a more seamless transition between the two. Obviously that didn't work, because then the other table was updated and mine wasn't updated to reflect it. So absolutely happy to adopt that. The intent was that they would reflect the same information from my study's point of view, and from the groundwater point of view, the figures that I've generated or contributed to this table are around the average daily salt load, and I'm perfectly comfortable with those. There was a transposition error in those, and they've been updated. The remainder of it, which is around the total and the effect in the Murray, is where the baton change, if you like, happens from the groundwater project into surface water. I'm perfectly comfortable to adopt Dr. Treadwell's most latest set of figures on that. And the context in which I was asked some questions about the cumulative effect of the salt loads that I'd calculated, this table does address that. And strictly speaking, it's more of a surface water issue, but there is this overlap. So I wanted the two to be the same. So it is important and appropriate that we look at the same set of figures when considering that exchange.
And on the basis that this table is used or referred to in that context, is there any difference in terms of the opinions that you express, the conclusions that you've reached in respect of salt load and salinity caused by referring to this correct table or updated table by comparison?
No, none whatsoever.
All right, thank you. Apart from that, are there any corrections that you've identified as being necessary or appropriate to your witness statement, to the specialist assessment, or to the addendum documents that you wish to make?
No, there aren't any.
Do you therefore adopt those documents as your written evidence before this committee?
I do.
Okay. Now, thank you, Mr. Hoxley. You've then prepared your presentation, which I'll ask you to share on the screen and take the committee to.
Certainly. Stand by while I get the screen share working. All right. Can I confirm that you can see the front page of a slide pack for my presentation? Excellent. Thank you. Okay. Well, good morning, everybody. What I want to cover today is the groundwater specialist assessment related to the ER Central package, and its particular focus on Burra Creek. As Mr. Forrester said, the way that I've prepared this presentation is focused on the Burra being for the supplementary assessment, but not to downplay the rest of it, but just to note that we're adding this on, and the others haven't really changed. So this summary of the work that was undertaken, as we mentioned before, I was the discipline lead for the groundwater and hydrogeology assessment for ER Central. And I've also contributed to the supplementary assessment and the addendum document in relation to those groundwater and salinity related aspects that were in the original specialist assessment and are in the addendum. So that means that I oversaw the data collection, I oversaw the analysis, I participated in a lot of the analysis, and also had a strong hand in the writing of the final document. In the course of that, I've also reviewed all the public submissions relating to the specialist assessment, and I've responded to those, again, in my witness statement, and I've got a summary of that in this presentation. I've also considered the SIAC findings and the Minister's determination for ES Central and for matters that are relevant to Burra. I've got a response on that within my witness statement and a bit within this presentation. I anticipate that there may well be questions or further conversation of that later on, and I'm happy to respond to that. There were some components of the analysis that were undertaken by the broader team that was been working on this, and this work was done under my supervision, and the people involved are listed in my statement. And finally, just as a note on my experience on groundwater occurrence and behaviour, I've had a specialist study of groundwater within the Mallee region, and in particularly the interaction between groundwater and the Murray River in this part of the world for over 35 years. I've had a lot of experience in a range of projects and studies in the area, and consider myself very familiar with the issues and the response of groundwater in that area, and that's documented in my CV. The key issues that were identified for Burra Creek project related to essentially construction of the project and then the operation of the project. For construction, it's primarily and effectively only the drawdown of groundwater associated with construction. I'll talk a bit more about that aspect later on. The other issues that were identified with the development of the assessment was the potential for rising groundwater level over time in the floodplain in response to managed inundation. That is related to the possibility of forming areas of shallow saline groundwater. And a further part of that process is the mobilisation of groundwater to cause salt discharge to the Murray River. I'll talk about the assessment of these later on, but they were the issues that were identified as part of the initial assessment and the risks. To go to a summary of the key findings before I present the detail, we have not identified any high-risk groundwater effects for the Burra Creek project. There are some minor effects on groundwater. The groundwater responds to managed inundation, but these are not high risk. The effect of construction is essentially the temporary drawdown of groundwater associated with some of the structures that are close to the Murray River, particularly the drop point structures where flow is likely to return to the Murray. As you'd be aware, the detailed design and construction methodology for these structures is not yet complete. So we've taken a conservative assumption about the way in which you might dewater on the bank of the river in order to construct the drop structures. There are a range of alternatives. What we've presented is what we believe to be a likely maximal effect, and I would not at all be surprised if the actual construction had less effect than we have calculated. Overall, though, even with that approach, it's still a relatively small effect. The effective operation overall is the expected slight increase in groundwater level over time, particularly beneath, but also adjacent to the inundation areas and the waterways that are associated with the operation of the project. It's really focused on those areas of most frequent and deepest inundation in the north of the project area. It's an almost certain effect. If you run inundation, you're going to have a response, but it is a minor response. As a result of this slight rise in groundwater, there is an expected long-term increase in groundwater discharge to the Murray, which will carry this around 3 tonnes a day of salt over time. Again, this effect is almost certain, but it is a minor effect. I might note here that the salt load here is in relation to the salts that are already in the groundwater being displaced into the Murray rather than the salts directly from the inundation water, but we can talk more about that in the detail. There is expected increase in water availability for water-dependent vegetation. This is almost certain possibly beneficial effect. And the reason why I called it possibly beneficial is, again, there's an exchange here between the terrestrial ecology specialist assessments and groundwater. From the groundwater point of view, we expect and understand that there will be additional water in both the soil zone and in groundwater underneath the areas of managed inundation. This was expected to be available for water-dependent vegetation in those areas, but the actual complexity of how much they use and to what extent that's beneficial has been left to the ecologists to study, but we recognise that there is likely to be more water available for vegetation in this area. There is no expected change in groundwater quality TDS, and this is largely because the response, the managed inundation in its form and practice is effectively equivalent to a natural flood from a groundwater perspective. And the floodplain environment out there has already co-evolved with flooding in that region to have the groundwater quality and distribution that it has at the moment. And we're not expecting that to change as a result of the operation of the project. So in summary, the assessment report and the addendum document consider all the groundwater values that are in the EPA reference standards, and they do address all the scoping requirements. And we've also identified ongoing groundwater monitoring requirement during operation in line with the forecast effects. There are monitoring sites already in place, and monitoring will be undertaken by the Mallee CMA. I believe that the recommended monitoring locations are adequate, but I'll come back to this matter later on, and I'm fairly sure we'll have questions about this during discussion. Briefly about the scoping requirements, essentially the same for all projects in the central package, and they've not changed since for the supplementary assessment. And broadly, it's to look at the effects on hydrogeology, groundwater and groundwater-dependent ecosystems, to characterise those effects, to assess the likely adverse direct and indirect effect, and look at cumulative effects. And all of the scoping requirements have been considered and addressed in the documentation that has been provided and underpin this summary assessment that I'm giving today. To look at a bit more at the approach to the assessment, on the table on the right identifies the environmental values that may potentially be present in groundwater. So this was the start of the assessment to look at, is an environmental value present? For example, the final one at the bottom there, the geothermal properties, the water within the floodplain and within the project area is not of elevated temperature, so therefore there is no environmental value for geothermal property that needs to be protected within this area. All of these values were looked at, and the ones that were present within the area and need to be protected were considered in the assessment. The next stage was around looking for potential groundwater pathways to reach that environmental value or the receptor. And this is using the source pathway receptor model, where values are the receptors. The source is the process that is likely to or may affect the receptor. And the pathway is the specific project actions that could lead to a connection between the two. It's worth noting that without a pathway in place caused by the project, then no effect is possible. And we've looked at the pathways that the project would create for construction, dry commissioning and move together, and operation and wet commissioning are together. Finally, the comment here around the groundwater pathway in New South Wales, because the works are all in Victoria and because of the hydraulic effect of the Murray River in controlling water levels and being a natural break in groundwater flow, there isn't any pathway or effect in New South Wales. And so that means that there's not necessarily been a need to look at effects on the New South Wales side. The effect, I'm moving now to the effects assessment itself. We looked again at construction effects and operation effects. The construction effects looked at dewatering required to construct the drop structures. We did a risk assessment of where the structures were, what the depth to water table was, the likely depth that would need to be involved in any construction work or excavation. All the other structures are well above the water table and are not expected to intersect it. We looked at an analytical assessment of the drawdown depth and extent for those drop structures, assuming that to put the drop structure in, you needed to do works that would be at or below the river level, and that may require dewatering or clearing of water out of that site. Again, I note that the final construction methodology has not been totally finalised, so we've made an assessment based on fairly standard construction techniques that we think is appropriate and possible to be used. They can be optimised, and there is a possibility that depending on the river level and the actual operations, that the effect could well be much less than the one that we've adopted. Operational effects are focused on the managed inundation itself, and we assess those using a numerical groundwater model. It's not formally calibrated, but it was checked for response patterns against the monitoring record. It includes the effect of broad area inundation through the pump watering and then the distribution of that behind the structures, and also includes the effect of tree or vegetation water use from groundwater, which is another important draw on groundwater and helps result in the cyclical nature of groundwater response. I'd like to move now to the existing conditions statement, or looking at the existing conditions of Burra. As a note, there was no change to this assessment as a result of the supplementary work. The existing conditions are effectively unaltered. So in summary, the water table within the floodplain is connected to the Murray River. It's about 5 to 10 metres below the surface, and it shows a response to floods and high river levels. The shallow groundwater aquifer has variable groundwater salinity, which formed naturally in response to floods and droughts and a range of vegetation water use. And groundwater quality is fresh to saline within the project, mostly saline across the bulk of the floodplain, but fresh particularly along the edges of the river. Burra Creek itself is a recharge feature for groundwater. It is well above the water table and it doesn't receive groundwater discharge. And this is likely to persist even during the operation of the project, but at the moment you can see that the groundwater levels that we've got measurements for are quite a bit deeper beneath Burra Creek. It's what's called a disconnected recharging system. It was put together in a picture here of the hydrogeological setting, and on the left I've got figure 1116 from the specialist assessment report that shows in summary the groundwater and hydrogeological features. On the right of this though, I've put a figure that is a relatively recent satellite image of the region shortly after the floods of earlier this year. I just thought it would be helpful to relate where this section is to the photo here. But in short, you've got the Murray River, which is cut into the sediments around the area, and there is a relatively shallow here, which is referred to usually as the Monument Formation, but contains a mixture of sands and silts, but it is essentially directly connected to the Murray River. Overlying that is an alluvial clay, or the floodplain clays, and that is what you would see at the surface. In the floodplain clays, or in the alluvial clay, is set Burra Creek. The water table in this area is, at or just below the alluvial clay within the sands, and it's a little bit higher immediately under the floodplain, and depending on exactly what the river level is, this can move up or down. And it flows a little bit to the west, very slight gradient out to the west. But to the west, we have this unit called the Blanchetown Clay, which is a fairly heavy clay. It's regionally persistent across the area. And this is a significant barrier to flow out of the sands that are in this area. It's not totally impermeable, but to give you an idea, the permeability of this would be 1,000 to 10,000 times less than the permeability in here. It's a very low permeability, highly plastic clay unit that doesn't really move a lot of water. Now, this cross-section, for example, would be, if you looked across a region through where my cursor is, just checking, can you see my cursor moving on the screen there? Thank you. So if you look through this area here, you've got the river, you've got the grey floodplain sediments, you've got this on the photo here, you can see this sort of red sandy patch here. That corresponds to this high peak here. It's a lunette feature, or a windblown dune feature, that sits on the edge of this former. This lake is in dune sands, but also sitting on Blanchetown clay. So if you look at this zone from about here across to the river, this is the region in which you've got the aquifer. And looking at the grey floodplain, particularly this sort of darker region that was the flooded area, you can see the effective area of natural floods in the area in which this monument formation is concentrated, and how close it is to the river. And there you can therefore see also the potential for the direct connection. Once you get over onto this side and out onto this area here, you're on clays. You've got this high ground in between. There's essentially disconnected from what goes on in here. This is affected by the river and the flooding that occurs in the vegetation that's on the top of it. They're the main drivers. So to look now at the depth to water table, these are some more figures out of the specialist assessment. So this is figure 1114. The depth to water table range that's shown in the greens here is the 5 to 10 metre range. Perhaps unhelpfully, we've put the inundation areas on here in this violent lime green colour, which is also overprinting the general greener colour from the depth to water table. But suffice to say that for most of the area, all of the maximum inundation area where managed inundation will be applied, the water table is 5 to 10 metres. There is a relatively small area around what's called the town of Goodnight, New South Wales, in this area in here, where the depth to groundwater is a little shallower due to the geological conditions here. But where Burra Creek runs and through most of the actual area of open inundation, it's relatively deep. You can see the sort of lake feature, which has farming on it, which we showed on the other picture over here. And the area that we've done the depth to water table for mapping has the colour through here. What's our distribution of information through this site? I've got here a figure that shows both the recommended monitoring wells, but also other monitoring wells that are available in the area. And for a relatively small area, it's pretty well served with groundwater information. We've got essentially two groups of bores. One is a southern group along here that includes a section line that goes away from the river in Victoria, but also bores around this Goodnight region. And in the north, we've got a series of other bores that are also along a section line. There are a few other wells. This one here is related to the monitoring of this irrigation area. And there are a couple of other wells in through here in the middle of the project area that have been installed by the Mallee CMA specifically for the purposes of potentially monitoring the inundation area and the inundation response. So for a fairly small area, it's pretty well served with the amount of groundwater information and hydrogeological information we have. From this well set, we can look at groundwater salinity. This map here is a combination of the results of the airborne electromagnetic survey from the early 2000s, plus the bore data that is available, showing the range of groundwater salinity at the water table. And you can see here, a key feature of this is that along the river, the groundwater salinity is relatively fresh. There's sort of what you might call as brackish, so 1,000 to say 5,000 within this region right against the river. But when you move into the floodplain proper and the area of the inundation, the salinity starts to rise. So it rises up to say between 13 and 20,000, or perhaps over 20,000, up to 35,000 milligrams per litre. At the range of 20,000 to 35,000 milligram per litre, most of this groundwater is not accessible by deep-rooted vegetation just because of its salinity. If tree roots get down into this, they really don't use this water to any significant extent. They may very briefly in very bad drought situations. So realistically, the bulk of the area where groundwater-dependent vegetation is going to be regularly drawing on groundwater is the area of the oranges into the blues that are shown through here, but not the sort of this yellower, but not these deeper colours. And you can see the bores here, the dots that we've got in here with the colours in them represent the bore data that we've got, as opposed to the more distributed AEM data. This chart is a bit of an amalgam of a figure from the original specialist assessment, but also the addendum report. And what I've done here is show the groundwater response at a bore. So I'll just go back a page. The bore that I'm interested in is the one at the north of the project area, right adjacent to the Murray River. That's part of the section line that goes along the northern end of the project. So this bore is pretty close to the Murray. It is up on the floodplain, and the groundwater elevation is shown on the left-hand side of the axis here. So it ranges from about 51.5, potentially up to 56 metres. So sort of 4.5 to 5 metres fluctuation. The key thing that I'd like to draw to your attention here is in the 1980s through to the mid-1990s, there was relatively frequent variation in the groundwater level. This variation started to drop off, and then through particularly the millennium drought, we had much less response to river level. And then as we come further out here into the around 2005 to 2015, one thing that happens is that the frequency of reading drops off. So you can see here that they're relatively frequent, and here they've become less frequent. But you can also see here that the 2011-12 flood or higher river flow periods do show up in the record here, but the groundwater bore record just misses the 2016 high flow event. Now, this has been compared with the river level, and in the original report, the river level was shown was Swan Hill gauge. But given the changes and the whole reason for the supplementary assessment, I wanted to show this against the gauge at Warcool. Now, the river level at Warcool, the gauge is not formally surveyed, so I don't have a measurement in AHD, but I've got river level above bed level for the gauge, which is good enough for this purpose. But what you can see here is that at Warcool Junction, the Murray River's got a very similar sort of up and down pattern that we see in the bore through here. Now, interestingly, the level here is, say, from 47 to 50 metres, 3 metres, maybe 3.5 metres. The groundwater level, when you come a little bit back upstream, is a little bit more than that. And I think that's the result of this confluence of both a flow coming from the Swan Hill Reach plus the backwater effect coming up from Warcool Junction. But this record shows a very similar pattern. You have through the 80s into the start of the millennium drought in the mid-90s, relatively regular, frequent high flow events and overtopping events that will lead to a groundwater response. They then drop off. You get less of those. When you do have a big flow, you will get a groundwater response. What I would expect without the project in place is that we're going to see a groundwater level that's fairly static with small responses to individual river flow events, but generally fairly stable. With the project, they're going to be introducing more managed inundation, and that is going to take that response to one which will be more akin to this period. So in the 1980s, we had more regular, close to annual high flow events. So what we will see is that the groundwater level will rise and fall more regularly, and it will probably be on average slightly higher than it is here. And this is exactly the pattern that we've seen here. It was up and down more in this period. It was on average higher in this period. With my expectation of the without project effect is that the groundwater level will reflect this sort of more static, lower condition. And by putting the managed inundation events on, you will see more variability than you would if you didn't have the project. It's not, if you like, an unnatural condition, but what it is done, will be caused by the project. So it is an intervention. It is something that the project will do. But this is one of the reasons why the effect of it is relatively minor, because it is a condition that this landscape has experienced in the past, not that long ago, so in the 80s and 90s. So looking at the risks, the identified risks are considered low, following on from that conversation. The risks relate to flow changes during construction or operation and quality changes during construction or operation. The risks identified during construction as minor. The disposal, effectively, there may be a little bit of dewatering for a short period of time associated with construction. Because of the connection to the Murray River and the capacity for the system to respond to river flows, that will recover very quickly. And because the construction period should be short, it will be a relatively small effect. The disposal of dewatered groundwater is insignificant, largely because the dewatering is right on the banks of the Murray. That's where we have the freshest groundwater. There are multiple potential options for disposal. Typically, where structures have been built on or near the Murray River, the disposal is back into the Murray River. But in this case, because the groundwater is so fresh, the effect of that from a salinity point of view is minor and essentially insignificant. There's the possibility for spills or contamination from construction, but there are well-known methods for mitigating that or controlling that with construction approaches, and so the risk for this is minor. And there is an effective groundwater level rise over time as a result of the inundation. But again, this effect is a minor effect because this landscape has seen this behaviour in the past, and it will be taking it back to that type of behaviour that it has had previously. In part, the rationale for the project is to restore a more natural flooding equilibrium, and that's effectively what that's going to do to the groundwater system as well. So the summary of effects in some pictures: the construction, the dewatering for the drop structure, probably 2 to 3 metres drawdown. The figures are in the specialist assessment. Relatively short, few weeks in practice. But we've looked at it for a number of months to get a maximum effect for the potential construction. And again, that is minor. The change in shallow water table level, this figure here from the addendum shows the area that we would expect to have a shallow water table that is less than 2 metres below surface and the period of time. We've got a small zone up near the deepest part of inundation that may have a water table less than 2 metres for up to 20% of the time, between 0 and 20% of the time. Essentially, that's associated with the periods of inundation. So where you hold water in that area, you would expect that the water table would rise. If it's there for several months, it could very well rise up towards the surface. We have water at the surface. Then when that's released, the water table will start to respond, will drop away. In some senses, it may drop away where the soil water is fresh enough because of the effect of vegetation water use, or it will just drop away because of the permeability of the aquifer and its connection to the Murray River. It will naturally just drop back. So there is an area in the northern part of the study that will see more frequent shallow water table than if the project wasn't there. But this is not considered a large risk because it's a short period of time. Looked at the potential effects on vegetation water use. They're relatively minor. So in here, this figure shows the ET increase for the period that we've modelled. That's from 2000 to 2020. And we looked at the cumulative ET increase in metres. Now, if you understand that evapotranspiration, like rainfall, is measured in millimetres, But if you add all that up over many years, you can convert that to meters. And so this is a fairly small effect. You can see that the effect is over 20 years is typically less than half a metre. It's a few percent of the overall water balance. It's a small, possibly beneficial effect. I don't want to overplay it, but it would also be wrong to not acknowledge that there is actually the potential for this water to be available where it's fresh enough. So it is an effect. It is a small one, though. Cumulative effects. The only identified cumulative effect is the increased salinity in the Murray River, and that is likely to be accountable under the Murray-Darling Basin Salinity Management Strategy 2030. The increase in salinity following a managed event in real time is probably about a half an EC in the river. And we would expect that this increase in effect is already present. I would have expected that following the floods earlier this year that we would have seen salt load increase in the river above that as a result of a large event, and that would occur all the time. And so it is unlikely that this is going to have any significant effect on the rivers, and because it's there already. But when you can look at overall salinity at Morgan, because the Basin Salinity Management Strategy is about adding up all the cumulative salt loads that are put into the river and accounting for them towards the end of the river at Morgan, we think that there is an estimate of about a half an EC at Morgan that could be contributed by the operation of the project compared to the no project case. For a whole lot of reasons, I believe that 0.5 EC is going to be an overstatement of the final figure that would be put on the registers. There's a process involved, very specific process about determining the final figure that relates to the protocols that are under the Basin Salinity Management Strategy. The estimate that we've provided is not completely compliant with those protocols because they will be done once the project is completed. And so I've got an estimate of that where we've been conservative and used higher figures to give an indication of what the likely upper estimate would be. So my expectation when the final assessment is done for the protocols, then it's likely to be lower than that increase. Either way, it is a small increase. The effect of that is likely to be offset by existing salinity credits that are held by the state of Victoria, is my understanding. Again, that is to be decided by the Basin Management Group and by the state once the final effect is known. We now come to this table that Mr. Forrester referred to you to earlier. I'll leave the discussion of the cumulative effect in the Murray to Dr. Treadwell, but the point that I wanted to make here is that in the context of the other projects, Burra Creek is a small one. It's not the smallest. Generally, the salinity effect increases as you go downstream. So when you get to EES Central, for example, they're larger numbers, and you go down to the estimate at the moment for Walpolla and Lindsay, they too are fairly large. You go up to, say, Gunbower or Guthrie Benwell, they're relatively small. The groundwater is relatively fresh. The Burra Creek project sits somewhere at about the transition zone into the more saline environment of the Mallee out of the riverine plain. And so it's starting to get in that cusp where it's starting to pick up, but it's still not a large number. The changes to the table that Mr. Forrester referred to before don't affect my assessment. The assessment that we've done is the input to this, and I'm completely comfortable that the numbers that we've got aren't changed by the changes in this table, and that I've used those for the assessment. So, summary, back to key findings, which showed this slide before. There's no high-risk groundwater effects identified for the project. There's a temporary drawdown for construction of up to 3.5 metres at most, based on a conservative methodology. And the effective operation is the expected slight rise in the groundwater level over time beneath the inundation areas and in the adjacent areas, a small long-term increase in groundwater discharge to the Murray River, a small increase expected in water availability for water-dependent vegetation, and no expected change in groundwater quality or TDS. We've looked at the reference standards, we've addressed the scoping requirements, and we've recommended monitoring for the Mallee CMA. We'll move now to the environmental delivery standards. EDS for groundwater the GW1 and GW2 deal with the effects of construction and operation, and I think they are suitable. Sorry, that sounds too weak. They are suitable for managing the groundwater effects, particularly given the low impact on groundwater identified by the project. The operation of the EDS is underpinned by ongoing and appropriate groundwater and salinity monitoring. We've got recommendations for that monitoring, and as I said before, we've got a pretty good spread of groundwater bores available to do that monitoring in this area. Monitoring of both natural and managed events will enable responses to be better understood. And one of the reasons for the frequency of the monitoring over time and it not being related just to the managed events is it's good to get that baseline of all events so that you can put the managed events in context. And the monitoring recommendations have been provided in the documents. There are some submissions related to this project. There were some initial submissions by Environment Victoria. The question there was about offsets and whether they'd been relied on to reduce the effects that have been assessed. And I want to assure you that the assessment of the effect is prior to the offsets. What I'm suggesting is that the salinity credits under the BSM 2030 strategy would be used to offset the effect and the effect as calculated. And there was a question about the maximum possible salinity on the Murray River of all 9 projects. And that's related to that table that we were referring to, and I'll again defer to Dr. Treadwell to pick this up overall when he talks about the surface water effects. If the projects aren't operated at the same time, it doesn't devalue or discredit that table in any way. It just makes the effect even less that has been calculated at the moment. There were some further submissions. The EPA identified the typographical error that was at the heart of the discussion about the salt load table. There's a question here about the level of effective salinity requiring further justification. I've responded to that in my statement and saying that the effect of the increase is really small. It's only just above the sort of significant level threshold for reporting. And it's not considered to have any ecological effects in the river. So it seems that given the threshold nature of the effect, it appears to me that that level effect is appropriately justified within the reports. Environment Victoria has concerns regarding cumulative salinity effects, particularly talking, I think, about the Coorong and other downstream areas. The comment that I would make is that the effect of this project is very small. There are many other effects in the Murray River along between here and the sites that they've identified, such as irrigation salinity return and a range of other natural processes. It's the total cumulative effect of the salt load is taken care of through the BSM 2030 strategy and the overall management of the Murray, so that is allowed for. And it doesn't seem to me that these projects represent in any way any significant threat to those downstream areas. Again, I'll defer to Dr. Treadwell's assessment of the in-stream effects. And the presentation.
From Mr. Hoxley. Can you please turn your cameras on now? Okay, looks like it might be just questions from the committee, and we haven't got all that many questions for you. I just wanted to ask a general question first, and this is something that came up in your verbal presentation there. I just want to understand how deep-rooted vegetation responds to the presence of saline groundwater. So you mentioned that if it's there and if it's in contact with saline groundwater, it doesn't use it unless it's like a millennial drought type situation. How does a tree root know whether it should be absorbing that water or not?
Yeah, good questions. So typically what we find is that the root zone of trees where the water is saline and always saline, the roots traverse down until they find that salt water, and then they stop and they don't go much further. So typically what you would see for vegetation that's sitting on top of shallow saline water table is that the root zone will be concentrated in the soils at the top and won't go very deep. And the reason for that is when the roots go into that water, the whole reason that they don't use the water is because they can't drive the osmotic gradient to get the water into the roots. So what happens with vegetation is that they will take the water out of the soil but leave the salt behind, which means that they use effectively an osmotic or membrane transfer to bring fresh water into the plant and leave the salt behind. When the groundwater salinity gets too high, and this is dependent on particular species as to exactly where that limit is, but as the groundwater salinity gets higher and higher, the vegetation is unable to overcome the draw of the groundwater on the water, and it can't take the water out and leaves the salts behind, and so it's not available to it. What that means physiologically is the plant stops growing roots in those areas where it can't get water. Yeah. So it will move down to the point where it can't get at water, and then typically they'll stop. Now, what we've seen in the deeper mallee and in some areas of research to the west is that there is an indication that as an emergency drought reserve, in particularly dry periods, trees can force themselves to use water that they mightn't otherwise like, but there is an upper limit to it. And on these floodplain environments, because typically there is fresher water available, you don't really see those deep, very deep roots sitting in saline water waiting for a bad drought. They'll concentrate the root mass in the upper part of the profile where you can get fresh water from floods and harvest most of that.
So with the graph you showed us of, and you explained that you expect with the inundation, increased frequency of inundation, you expect the groundwater table to start fluctuating more like it was back in the 80s and before then. Are the levels of salinity in the groundwater in this Barrow Creek floodplain high enough to impact on, so if the groundwater table came up into that sort of shallow rooted system, would that impact the vegetation, or are the salinity levels not high enough to pose a problem there?
Oh no, it's a good question. What will happen if saline groundwater that the trees can't use comes up into the root zone is that they'll effectively turn off those roots.
Right.
The roots can persist for a period of time. If it becomes shallow for a long period of time, then the roots would die back, and that would have the potential to affect the tree. And this is where the mapping of low to high risk of salinisation comes in. Now, we've identified in these areas that because those peaks are quite transitory, they only occur for a short period of time, they're not considered to be a risk of affecting the vegetation, in that they can cope with getting their feet wet with salty water for a short period of time, particularly if that's associated with other fresh water being available in the soil above it. Then when the water table drops away, those roots will come back. As a general rule, the plants don't grow their roots into permanently wet areas. They don't like waterlogging. They'll use a bit, they tend to grab the stuff off the top of the water table rather than going all the way into the deep of it. So they work at the interface. In that interface, you always have fluctuations of groundwater up and down, so the roots can cope with that. So the key thing here is shallow saline water table developing for short periods of time is not inherently a threat to the vegetation, but if it develops for a long period of time, then yes, it could be. It could either cut back on the available root space for vegetation, or it could become active in the capillary zone and draw up to the surface. We've not identified that as occurring at these sites.
The next set of questions we've got for you are around monitoring. So you predicted that correctly when you said that you thought there might be some questions around monitoring. I think the EDS proposes annual monitoring for salinity. And you did mention that you want to get a pattern of sort of baseline conditions, and so you can place the salinity levels resulting from the project in that baseline. Is annual salinity monitoring sufficient for an adaptive management approach?
Look, I believe it is because where we've looked at salinity in the Mallee and the response that it has, it doesn't on a month-to-month basis. There are long-term trends. The groundwater salinity is quite stable. You can come back to it year after year. Bores which are immediately adjacent to the river may change a little quicker, but again, typically the average salinity that you would get at that location won't shift over time. So, for example, with all the monitoring that we've got in this area, what you don't see is an area under the floodplain going from 1,000 milligrams per litre in the groundwater up to 30,000 and back down again. What you might see if you've got an area of 20,000 or 30,000 milligram per litre groundwater is it might be 20 this year or 21 the next year. It's quite stable. And because of the processes and the fact that you have to change it, you would have to have salts migrating down, you would have to have mixing in the aquifer, and these are slow processes. So looking at salinity over time and all of the water quality parameters over time and on a manual basis, I think is adequate. And the other thing is that the project is unlikely to operate every year. So many of them have 1 in 3 or 1 in 4. So you're still doing several monitoring events in between the actual operational events. So you should be able to see if there's a change after those. Well, there have been some attempts of a research nature to look at the detail of the groundwater salinity variation immediately adjacent to the river. At one stage, we put a bunch of loggers in the Murray River down near Weeman, just downstream of Euston. Again, they do vary around a little bit, but the average stays pretty close to that value that you get. And so if you wanted to see whether or not there was a change in groundwater, then that annual monitoring is going to give you those trends. If there was something that adaptive management needed because it saw a change that needed more information, then you could definitely step that up. But at the moment, we're not expecting any change. We don't see that there are processes there that are likely to lead to a significant change. So from that point of view, there isn't an obvious threat that I feel that you'd be missing by not having more frequent monitoring, and hence I think animal is adequate.
Would that change if, so some of the VFMRP projects are in more saline areas like Belsar, Yungara, and I think it was Lindsay Island. Would you give the same answer if we were talking about one of those areas? Does it depend on the sort of background salinity levels?
No, largely they are fairly stable. And I think the history of monitoring across those areas is such that I'm comfortable that they don't vary much from year to year. I've got some bores that are in the Mallee and the Stack, and some of them I put up on the screen before that have had EC monitoring from back into the 1980s. In fact, there's some levels or graphs of the EC responses that we've got that were put in the specialist assessment. And there are some fluctuations. Some years go up or down, but they don't change to the same extent that the levels do. Having said that, if you want to go down to, say, Lindsay Island, I could well see, given the scale of the structure and some of the processes that could go on there, that there might be some points that more frequent monitoring is worthwhile. That's probably as much related to the return salinity. So one of the things you want to know, say, at Lindsay Point, for example, would be what's the salt load that's actually going to come back into the river after an event. And so you might either put a logger in the creek or one in a groundwater bore to look at that process in a bit more detail. There isn't that level of threat for Burra, so it needs to be looked at for each site, but these upstream sites don't appear to warrant that risk. We don't have that risk that will warrant that response, rather.
I don't know that I'll need you to pull slide 12 up, but slide 12 has the location of the monitoring bores on it.
Yes.
And there's only 2 that are located within the maximum inundation area.
Yes.
Is that sufficient?
Given the area involved and the processes that are there, I think that will give you an understanding of the way in which that maximum area is responding. So I'm comfortable that there are sort of 3 bores within the vicinity of the MIA, 2 of them quite close to it, which will show you the response to either a natural event or a managed event in that area. I don't think the risk is such that you need to be looking at several different locations across there. The water table's relatively deep. We have some response that shows the way the pattern is. The purpose of these bores, in my view, is to confirm that the groundwater is responding as is forecast and as is expected. Now, if it was doing something that was unexpected or unexplained, then that may trigger further monitoring or investigation of that as part of the overall adaptive process. But in the first instance, it doesn't appear warranted.
Okay.
There isn't a risk or a threat there that would make that, to me, seem to be worthwhile.
Are all of the recommended monitoring wells for Burra Creek in the shallow alluvial aquifer?
I think so. I'd need to go back and check exactly. One of them that is out, there's a couple of them out to the west of the region, which I think there might be a couple that are in the deeper aquifer out there, as the shallow alluvial aquifer doesn't persist out to the west. And yet I have recommended monitoring some of them in that deeper aquifer, which is the only aquifer out to the west.
Okay. Actually, this might benefit from, are you able to pull slide 12 up?
I can. Press the share button, that helps. Hopefully you can see that now.
Yes. So see there's that sort of collection of wells, relatively sort of straight, through there.
Yep.
You've you've identified it despite my very poor explanation. Why the collection of what is that following an existing sort of transect of monitoring wells there? Why are they
That's
all
right.
in that sort of?
In the 1980s, there was a study of the groundwater in this area that put in a number of background groundwater wells, and there's 2 what were called the section lines as part of that study that put the initial work through here. One of them goes out through here, which is largely picked up with these wells.
Yes.
And then there's another section line that goes through here on the Victorian side. Now, this aggregation on the New South Wales side was done as part of salinity management investigation work about the nature of the Parilla sand and its connection in this part of the world. When was that done? Probably in the 90s, but some time ago. So there was a more intensive investigation done on the New South Wales side of the river, looking particularly at the Parilla sand and its relationship to the aquifers in this area. That the Parilla sand is the deeper aquifer. The existing monitoring on the Victorian side had provided sufficient context, and so that predated this work, but there wasn't information on this side, so that's why they were spread around in here. But this information already existed, and that was used for the Victorian side to put context of what's happening in this region.
And I mean, I guess you've already sort of answered this question, but my understanding is that the monitoring that's proposed for this project will only use existing monitoring wells, not proposing any new monitoring wells. Just given the sort of nature of the project and the area it's covering, you don't think any additional monitoring wells should be established?
No, because if you look at these bores in the middle, like the WRK 119 series, there's 3 bores in here. The Mallee CMA went through a process about 3 or 4 years ago of saying, well, where might we have some gaps that are around the VMFRP projects that could warrant extra wells? And they were installed, and they exist already. So prior to these going in a few years ago, there was the section line up here and the section line down there. It was the project was looked at and said, well, what else might you need? These wells were put in. So with the fact that there has been additional monitoring put in specifically with having regard to the project and its likely effects, and that's already in place. My view is to monitor those and the existing bore and the other bores around them, and then determine from that as to how it's going and whether that's adequate. So, no, I haven't recommended any additional bores. We had a conversation about this when we had the earlier version of the roundtable. As a scientist, I'm not opposed to additional data and information. So please don't get me wrong. I'm not saying that there's no point in additional bores, but there is a balance between what you need to do to get into these environments, to get rigs in, to put bores, and where you put them, and the data that you get out of them. I felt that given the risks of this project, that this spread was an appropriate balance. If more bores were recommended or more bores were needed, they could be done. And the more you've got, the more reliability you have in the assessments that you make. So more data is always useful, but it comes at a cost, both an environmental cost and a resourcing cost. And it's about where you put that balance. And I thought the balance was right.
Okay. The EES Central Committee recommended more monitoring of salinity in the same location as the trees.
Yes.
Because they felt that would provide a bit of a leading indicator and would inform that adaptive management approach. Do you think that there's anything about the conditions in Burra that would make that a sound and sensible idea?
No, for two reasons. One is that in EES Central, the sites that were picked up are the ones that were regarded as moderate or high risk for developing shallow saline conditions. And that appears sensible, that we've got some sites that we've identified as higher risk, and to put some monitoring in there to confirm the behaviour there, it appears an appropriate recommendation. We don't have those heightened or higher risk areas within this project. Mm-hmm. We've also got some of these bores that are, in and around the vegetated areas. So some of the new ones that are referred to, close to the Murray River, close to the red gums, they will give an indication of what the groundwater response is in the areas that are vegetated. So I think, in absence of an area of specific risk, there are bores in here that do give you an indication of what the groundwater response under vegetated areas is.
Okay. My last question might be a question for Dr. Treadwell, but I'm going to give it a whirl anyway.
Sure.
Is there any monitoring of overall salinity loads in the river itself proposed? And if so, could you just point me to the right EDS? And if not, could you explain why not?
Oh, yeah. So I'll answer that in part and then pass to Dr. Treadwell. So as part of the groundwater study, I recommended monitoring of surface water salinity loads, and one of them was at the regulator for the outfall for the project. So that was to pick up the project effects. In terms of the Murray River itself, there is dispersed regular groundwater monitoring. So there's stuff at Swan Hill, surface water monitoring. There is a gauge at Boundary Bend. There is EC monitoring, if I remember. There's a telemetered EC station at Boundary Bend, which is, what would that be, 20 or 30 k's downriver from here as it goes around the corner. So in terms of aggregating the effect after the Waikul comes in, I'm not aware of any surface water monitoring upstream of the Waikul that would go in here other than what we would put in as part of this project at the structures. But then I'll defer to Dr. Treadwell to fill that in case I've missed something.
Okay. Thank you. Any further questions from Member Briscoe?
Yeah, just a couple of points of clarification in relation to some of the slides and some of those answers. And I'd just like to go back to the slide with the locations of the monitoring sites.
Certainly.
And with those, I guess I was interested in understanding, and this might be a question I notice as to, I guess, which formations each of the recommended monitoring sites targets. So can we infer from the ones that are sitting on the floodplain that they are actually going into the alluvial aquifer, or are they going deeper into the Parilla Sands? And those further off the floodplain, are they in the Parilla Sands?
Yeah, look, good question. How about I take that on notice? But as a general rule, comment is correct. The ones that are on the floodplain here have been chosen to be in the shallow alluvial aquifer.
Yeah.
I will give you a list of exactly what formations are monitored. We have that information. It was taken into account as part of the monitoring. I'm sorry, I just don't have it to hand at the moment.
No, that's okay. No, I thought it would have been. And I guess my question is, some of the sites clearly are in areas where there's perilous sands and not alluvial, and just I'm trying to understand the rationale for monitoring the perilous sands as well as just the alluvial aquifer.
Well, as part of the understand the overall regional connection and the gradient, however, showing the conceptual model early on. Where did I put that? There we are. And so the idea that we've got generally a slight shallow grade away to the west in here is really to pick up and confirm that those conditions remain stable over time.
Yeah. So it's sort of belts and braces approach.
Yeah, because everyone then asks the questions about, well, what else is happening in this area? And one of the other features or things that people have asked about, they noted the proximity of agricultural areas and one to the north. And so there is a question here about the interplay between these projects and the effect of irrigation in the region. From my point of view, they were to enable you to draw those lines and for people in the future to understand the relationship between what the irrigation might be doing and what the project, where the project is.
Yeah, that's good. And in terms of groundwater interaction, your conceptual model there shows groundwater moving out of the monument formation into, I guess, into the Blanchetown clay.
Yeah.
Is there movement the other way as well, or is it more that one way movement?
Well, because of the gradient, we believe that the flow is out and to the west. So the groundwater within the Perilla Sand and within the Blanchetown clay, as you go to the west, drops away and in towards, there's some discharge features in the middle of the dryland out to the west. And so generally there's a grade away from here. So no, there isn't really a response in this area. Other parts of the Murray there is, for when you get up, how can I show this best? Yeah, so can you see this irrigation development up in here to the north of the project? There is some response of this irrigation, and particularly when you go to the north, there is a lot of irrigation development in this part of the world, and there is particular interest in the effect of that on the Murray River.
Yeah.
It is worth saying that in this region, that effect is quite subdued, but there are locations along the river where irrigation can affect the Perilla levels and may move water back to the river. And it's worth keeping an eye on those regions that, because of the location of the Burra project and the conditions, the hydrogeological conditions, that's much less of a concern. But it's something that in background, I think as they're monitoring and tying this into the broader environment, if I was doing that work, I'd want to be making those links and just checking.
That's good, thank you. The next question is to do with the on slide 14, where you talked about the effects of the interaction between the groundwater levels and the Murray River levels. Yes. And I guess you were suggesting that the groundwater levels reflect the variations of flow in the Murray. You also showed in your conceptual model that Murray is fairly closely interconnected with the groundwater, because it's actually into the aquifer, whereas the floodplain is really sitting on clays above the aquifer. So would you expect a similar kind of response in relation to the watering of the floodplain if that watering occurs independent of a river flood, say a pumped inundation event, or would the clay be, I guess, slow down or prevent that occurring?
No, the alluvial clays will wet up, and I would expect that it will move through the alluvial clays and into the aquifer. And then if the river level at that time, for example, was low on my diagram here, if the river level was down there, then you would expect that to push groundwater into the river. And that's in large time the reason why we've got that salt load, the overall salt load going into the river, is because if you do a pumped event at a time in a spring when the river is otherwise quite low, you may get that effect. Typically, though, if the flooding or the managed inundation is done in spring, that's usually a moderate to high river level. not a lower river level, but it doesn't rule out that in a dry spring, if you wanted to do an inundation, you could have an inundation corresponding to a low river level.
Yep. And would that inundation then lead to higher salinities in the Murray River because they'll be flushed out?
Well, what it will do is it'll create a gradient which will then allow for water to flow into the Murray. The first water that flows in, of course, is that very fresh water that's adjacent to the Murray River. Now, for the purposes of calculating the salt load, I've assumed a salinity that is in the brackish zone, so it's relatively high compared to what we actually see against the river. So for short periods of time, what you'll get is river water coming back essentially. But if that persists a long period of time, you will get slightly more saline water coming in. Again, that's the process that we've allowed for, and that's the calculation that we've made in terms of the salt loads in tonnes per day. So overall, do I expect that to be a concern? No. Is it a process that we would have seen? Again, we've probably already seen it this year, and we've got it right now from last year's floods. That doesn't necessarily cause a noticeable effect that people are seeing, but I would expect we have salt coming into the river from a higher aquifer at the moment, and that would happen after some of the managed events as well.
So in terms of the, I guess the salt coming to the Murray River, have you looked at the gauging data, the salinity gauging data at Waikul Junction?
There was a water quality data point at Waikul Junction that had a limited record. So yes, I looked at it, but because it was relatively short, I ended up not using it.
Yeah, I'm just sort of interested in the sort of more recent salinity because I guess it's showing, and it's on the MDBA website. It basically shows quite a large salinity peak associated with the flood that occurred sort of last year into this year.
Yep.
And then there's a smaller salinity peak, but still quite a substantial one, sort of April this year, which seems to be associated with only a tiny rise in river flow. I'm not sure. No, I'm assuming from, I guess, your action, you haven't seen that, but I was just interested in sort of what you thought of that in relation to, did that mean anything in terms of how we interpret the effects on salinity?
I think that type of response that you would see after a major flood event is what you would expect. I'm really interested in the actual numbers, but unfortunately I haven't done an analysis of it. Would like to. I think that tells us things about the way that the system responds. In general, without having analysed the data, but in general, what you would see in the river is during a flood event, you will have a lot of wash off and then draining of broad areas immediately after the peak. And so that tends to bring salts with it. What happens then as the river continues to recess is that you get a mixture of either groundwater coming back in, or sometimes what you get is the draining of some of the billabongs and other features that were a little slower to get out of the system. And so then you get this immediately after the main peak's gone through, you can have this slower, more gradual response, which is a function of both groundwater and delayed surface water sources. And there can often be a lot of salt associated with that, whether it's collected off the floodplain or whether it's accumulation of groundwater across the whole area. You'd need to analyse it to understand it, but I'm not at all surprised to hear that pattern has been seen, say, a little bit after the 2016 event, but also after, say, the 2011 events, and then going back into the 90s after some of those events there as well.
Yep. And I've just got a final question in relation to the area. On slide 18, you've identified an area of shallower groundwater. And my question there was in relation to what the salinity, how that shallower groundwater interacted with the existing groundwater salinity in that area.
Yeah, so the existing groundwater salinity in that area is shown, where I'll get that up here, on page slide 13.
Yep.
So bear with me for a tick, I'll just put that up. So I'd have to flick backwards and forwards between the slides here, but the area that was identified was broadly in this region here. And so there's a bit of a mixture of some higher salinity water and some lower salinity water in that. I would expect that what you would see is that this slightly fresher zone here could be related to repeated flood events in this part of the world. And so you may see that pulsing a little bit in response to those shallow events, but it's all, relatively saline. It's getting up there. This is getting a bit beyond the tolerance for red gums for most of this area. Black box can still use it, but the red gums are mostly along the river here anyway, as I understand it. So this is more of the lignum box wetland EVCs. So some of this is able to be accessed by vegetation, I would expect.
And so in terms of the monitoring sites, and again, it's a matter of just understanding how the sites overlay, is that covered by any of the monitoring sites directly within that area?
Bear with me while I go and get my monitoring sites. So the closest one we would have here would be this side out here, or the two along there. So it's sort of straddled by those two. Excuse me, this would be probably in that slightly less saline area, would be this bore here.
Yeah. So if we were particularly interested in what was going on within that area with the highest I guess, shallowest groundwater and also the highest salinity, to really inform that, would there be value in putting an additional site right in the middle of that too?
Oh, it would certainly give us more information on the way that area is behaving.
Yeah.
In the end, you would probably model or reconstruct, using the available data. But if you had an extra point in there, you could be more certain about the response.
And in terms of collecting that data, I know we had a discussion before about, I guess, frequency of measuring salinity. Is there anything in terms of the process that will bring the water up to the surface, in terms of changing salinity fluctuating, being diluted or concentrated by whatever process is raising the groundwater at that local level?
So as it recedes, there may be a shallower, slightly fresher area, but it appears to mix fairly readily. So where we have bores on floodplains, what you get once the floodwater goes through is you don't really see like freshwater lenses or pods sitting on top of it. It tends to mix up. All the evidence that we've got is that in that sand aquifer underneath in the alluvial zone, it mixes up pretty quickly. So I don't think that there is likely to be seen a significant difference. The soil water over the top of it, so that water that's in the unsaturated zone, I would expect to be a little fresher than the groundwater, but then that will slowly percolate down, but it may get used by vegetation, or it may just mix with the groundwater as it migrates down.
So would there be merit, if there was particular interest in that one specific area, to say with the monitoring initially, with the first watering event, monitor the groundwater levels and the salinity at a sort of fairly high frequency, let's say monthly or something, to see if or how that responds, and based on that make a decision in the future to just continue with annual monitoring or persist with monthly if there is a response at that scale?
Yes, there certainly could. A question that I'd ask then is, does it need to be a permanent site, or could you do it by doing a temporary auger hole or something like that go in and do soil samples and test some soil samples for the first couple of events, and then see whether you need to do it in the long term? So I am quite conscious of the appearance of permanent sites with their tombstones and stuff setting up in the floodplain. So in principle, what you're saying, yes. How do you achieve it? Well, is it a permanent site, or is it some other testing that could be worked out? So, but the concept, yes.
Okay, thank you. And those are all my questions.
Thank you.
Dr. Kelly, do you have questions for Mr. Hoxley?
Yeah, just a couple, thank you.
Do you have I'm just trying to decide whether we should take a break now, or whether, so how long do you think you'll be?
Not very long.
Okay, let's go.
Yeah, sorry, before I was muted, I couldn't get on.
Well, good morning, Dr. Kelly. Good to see you again.
Yeah, good morning. Yeah. My questions were just a bit, could you give some context about in that area with you know, it's an agricultural area. So has there been any changes or impact, or what's the context of what's happening around the project site? So land use change, agricultural change, water changes in types of crops they're growing, and the way that's affecting the groundwater. Have you taken that into account, or could you make any comment on over time the changes that have been noticed?
Yeah, certainly. We did discuss this a bit before. I'm not sure whether you were on the call at this stage, but clearly within the
Yes.
what you might call the Burra Swamp, for want of a better term, I think that's the local name for it. There's the area which is the lake that's on the west of the Lunet. Maybe if I put the screen up, it might be helpful to just have a look at this. So we're back with this plot of the groundwater monitoring. So there's an area in here which has been farmed for quite a long time. It's relatively stable. We've got bores in this area, and we've seen the groundwater response. But this is on an area that's got blanchstone clay, which is the regional clay aquitard underneath it, and so there isn't any strong evidence of significant changes. And as I said, this has been around for a while. The area to the south, look, there's little pockets of irrigation down here. They haven't changed a great deal. There is a fair bit more happening, west of the highway and to the south. So there's some large developments there. There's also lots of large developments to the north, but specifically, regarding Burra, there hasn't been a great deal of change. You've got this site up here, which you can just see the southern extent of, that is, relatively recent, say in the last 10 years or so. So there are bores again around that show the response to that area. We've got bores on the floodplain that show the response in the floodplain. And there are a couple of bores like this one here, which were put in by the irrigator to monitor the shallow water table there, and a few others around here. Look, the nub of these is that the work that's been done to look at the effect of irrigation in this area says it's had a relatively minor effect on the alluvial aquifer in this particular region, and there's relatively little movement of groundwater or salt that's associated with irrigation development such as this. There is a little bit of an effect in the deeper aquifer going out in this part of the world that's carefully monitored, but for the purposes of this project, that irrigation development it has not had significant change on the groundwater response there. This aquifer in the floodplain is so well connected to the river that is by far and away the dominant effect on the groundwater within this region. And so, yes, we're aware of it. Yes, fully aware of the nature and the issues associated with that irrigation development. But no, I don't believe that it's a significant matter that would affect the project. You do want to keep an eye on what irrigation growth and other land use changes there are in the area, always with an environmental project like this. Yeah,
certainly the change from dryland farms turning to almond farms and putting water on the red soil, more and more corporates coming down towards Tullibuk, both sides of the river. So I was around in the 80s, so I remember all the stuff that was done on salinity, and it seemed to be a big problem. But now, would you say it's not such a big problem? And I see with the monitoring that you gave the table of in slide 12 that monitoring has dropped off in recent years, decades. Is that because it's not such a big deal anymore? Or what would you say that monitoring dropped off for?
Oh, look, it's really hard for me to say. I think that's probably a question to put to the Mallee CMA because they're responsible for that. There could be a variety of reasons. Sorry?
Did you not ask them?
I didn't ask them specifically why the monitoring dropped off. I just noted that it did.
What would you say you think it could be because of? Is it like what I said, it's not that big a deal anymore, or?
Oh, I
think it's not helpful to the committee to ask the witness to speculate on that.
Yeah, I was hoping he might not speculate. I was hoping he might have an answer, but that's okay. And what would happen? What would we notice apart from we would notice things on the bore monitoring, but would we notice anything if the groundwater started to rise not just because of the projects, but you know, what would be the things that we would notice if groundwater started to rise too much and get into dangerous levels? What would we notice on the ground?
So a really hypothetical question. I'll answer it for general purposes, but I want to make it clear that we do not expect that this process would occur in the project. But in areas, if groundwater raised came up close to the surface for extended periods of time, you would expect to see a couple of things happen. One is that vegetation that would be in that area may be affected. Its growth may be reduced depending on the salinity of the groundwater. If it stays very shallow for a long period of time, you can end up with waterlogging effects. So again, vegetation can have reduced health as a result of that. And in extreme cases, if you have shallow saline groundwater, you can get salt expression at the surface being brought up by evaporation, bringing it to the surface. So you can end up with salt scolds that can occur with very saline groundwater for protracted periods of time.
Yeah, yeah. I don't think I had any other questions. More so just to say, ask, is the more important about the groundwater level or about the salt loads, or are they both really important?
I think the two are tied together, so I wouldn't like to give one higher than the other. The salt load is an effect of the level response. In terms of being important, well, they're all part of understanding the way the groundwater system responds. So I think you want to have a look at both.
Yeah, thank you.
Okay, thanks, Mr. Hoxley. As I mentioned earlier, it would be helpful if you could remain online for the day in case some questions come up with Dr. Treadwell that we need to get your input on. But we'll take a break now and we'll resume at 11:50.
Certainly. Thank you.
Okay, Mr. Forrester, over to you to call or introduce Dr. Treadwell.
Thank you, Member Carlisle. I see Dr. Treadwell is coming onto the screen now, and I've got before me table documents B13 and B13A, his statement and presentation B37. Dr. Treadwell, I take it you can hear us.
Good
Morning.
Yep, good morning.
Very good. Your name is Simon Treadwell,
That's right.
and you're the author of a witness statement in respect of the Burrow Creek project dated the 4th of August 2023.
Yes.
Dr. Treadwell, you're also responsible for the preparation of Specialist Assessment C to the Environment Report, the ER Central, as well as the updated Specialist Assessment in Section 3 of Attachment 2 to the Burrow Creek Addendum. Is that
Yes,
right?
I am. Yep.
And can you confirm your qualifications and experience and matters required to be addressed by the Planning Panels Victoria's practice note are set out in Annexures A and your CV at Annexure B to your witness statement?
Yes, they are.
Now, you would have heard this morning me take Mr. Hoxley to the correction of a transposition error in the surface water assessment. And I understand, at paragraph, in your statement, you identify the same error and you provide your table 1, which I shared on the screen, as providing the corrected figures in respect of salt load. Is that right?
That's right.
And does the correction of the transposition error and does reliance on table 1 in your witness statement have any implications for the conclusions you reached and opinions you've formed in respect of surface water effects of the project?
No, it doesn't. The final numbers were not changed in terms of cumulative salt load. And so the transposition error doesn't have an effect or didn't have an effect on the outcomes of the assessment insofar as that cumulative salt load.
So the table was wrong, but the numbers used for the assessment were right.
Yeah.
Yeah, thank you. All right. Apart from that matter, are there any other corrections that you've identified as being necessary in respect of your witness statement, Specialist Assessment C, or the updated Specialist Assessment?
No.
And do you adopt those documents as your evidence in respect of the Burrow Creek project?
Yes, I do.
All right. Now, Dr. Treadwell, I'll ask you now to share your presentation and take the committee through it. Again, you would have heard a few questions of Mr. Hoxley this morning, which we'll try to address as we go, if you wouldn't mind. I'll remind you and share some things on the screen as appropriate and as necessary to do that. But for now, over to you.
Okay, I'm just, let me try and navigate the multiple screen. All right, can you see my PowerPoint presentation?
Yes, we can. Thank you.
Okay. I've got to try and get it working. Here we go. So I'll run through a summary of the work undertaken. I'll go into a little bit of detail on the reasons for the Burrow Addendum because I'm sure that there's some interest in that. An overview or summary of the project effects, the response to relevant submissions, and the proposed EDS. So the summary of work undertaken, I was responsible for the preparation of the Specialist Assessment C surface water and the Burrow Creek Addendum, and in particular planned and coordinated the technical assessments for surface water effects, along with other specialists who are noted in the expert witness statement. Co-authored the specialist assessment and the addendum along with the contributions from those other specialists. So I should note that there's in the specialist assessment for surface water, there's a lot of issues around water quality and hydraulics and erosion, geomorphological risks and things like that. And so I've relied on specialists in those areas to make their assessments and their contributions, and I've helped coordinate that work. And so in that context as well, in terms of providing expert witness going forward, I'll respond as best I can to questions, but note that, if there are specific detailed technical questions on some aspects, then I may have to take them on notice to go back to those specialists that were involved in the actual assessment. I've reviewed the public submissions and prepared responses relevant to surface water effects. I've also reviewed the site directions and prepared responses relevant to surface water effects, and I've prepared an expert witness statement upon which this presentation is based. So the Burrow Creek Addendum, or the circumstances leading to that, a review of the 2022 floods showed that inundation of the Burrow Creek floodplain can occur at a flow in the Murray River at Swan Hill at a lower magnitude than what had been previously determined. So we noted that the previous work that had been done and the advice that had been provided over the course of the, I guess, the development of business case and the development of the projects had indicated that a flow of about 30 to 35,000 megalitres a day at Swan Hill was needed to inundate the Burra Creek floodplain. Following the 2022 floods, with the benefit of, I guess, real-time flow monitoring and satellite imagery that is now occurring on almost a daily basis, certainly almost a weekly basis, the Burra Creek floodplain was observed to become inundated at a flow in the Murray River at Swan Hill of somewhat less than 30,000. And on investigation, we were able to identify that there's a backwater effect from the Wakal River that enters the Murray River further down. It's about 5 or 10 kilometres downstream of the Burra project area. And that backwater effect kicks in when the contribution from the Wakal River results in a combined Murray River flow downstream of the junction of around 50 to 55,000 megalitres a day. The actual inundation can start a little bit lower than 50,000, but to 55,000 threshold is about the level that is needed to achieve an inundation that's equivalent to the proposed managed inundation area. And that's actually occurring now at the moment as well. The flow in the Murray downstream of Wakal Junction is a bit over 50,000 megalitres a day. The flow at Swan Hill is about 23,000 megalitres a day, and we're seeing inundation of the Burra Creek floodplain at the moment. So those 2022 observations and the ones occurring now, I guess, sort of led to this identification of this backwater for that. Notably, when we look back through the hydrological record, it appears that when you take into consideration the Wakal River inflows, the inundation of the Burra Creek floodplain would happen more often than had been previously determined if you just used flow at Swan Hill on its own. And there's also some implications in terms of the backwater effect, creating as I understand it from the modelers, a shallower water level gradient across the floodplain than had been previously modelled. And I'll talk to those as we move through the presentation. So just in terms of the hydraulic effects, the review of hydraulic modelling that had been undertaken for the original assessment showed that sorry, I'll step back. We reviewed the hydraulic modelling for the original assessment, and then we've also reviewed some more recent hydraulic modelling that has been undertaken for the Reconnecting River Country modelling by New South Wales. And that Reconnecting River Country modelling is more up to date, and it is demonstrating or showing the effect of this Wakal backwater, and it corroborated, I guess, that we were getting inundation of the Burra Creek floodplain at that 55. I think they modelled 56,000 megalitres a day, but they modelled in sort of 10 or 5,000 megalitre a day increments, and their upper increment was 56,000 megalitres a day. But it's at around that threshold that there's inundation of the floodplain. We compared the water level elevations for the original modelling and the Reconnecting River Country modelling, and that's shown in this graph here. The dotted lines represent the water level through the project area when you only consider flows in the Murray at Swan Hill, and you can see that there's quite a steep gradient on the water level at this green one is about 20,000 megalitres a day at Swan Hill, and 30 and 35,000 megalitres a day at Swan Hill, and it's the black line is indicating the Burra maximum inundation extent, and with that original modelling showing that a 30 to 35,000 megalitre a day event at Swan Hill was required to achieve that inundation of the Burra area. But when you take into consideration the modelling undertaken by the Reconnecting River Country and the backwater effect, excuse me, We've got a much shallower water level gradient because this downstream water level is higher than was originally modelled, and the Burra maximum inundation area is inundated at a flow equivalent of, in this model, 55,900 megalitres a day downstream of the Walker Junction. And so in effect, what we're seeing is a higher downstream water level as a result of the backwater effect. And when we then compared the existing hydraulic modelling and the existing conditions from the reconnecting river country modelling, we can see again that there's this higher water level. These box plots represent the distribution of depths at various locations along the floodplain, and with the reconnecting river country existing model, we've got a deeper depth distribution in Burra Creek downstream of the B1 regulator. But for the rest of the floodplain, the depths are fairly consistent. There's some slight differences, but they're relatively similar across the middle and the upper parts of the floodplain, indicating that backwater effect is really only applying or having an effect at the very downstream ends of Burra Creek itself. We were also able to, extract some information on velocities from the reconnecting river country model, and the velocities from that modelling across the floodplain within the range of velocities that had been modelled with the original modelling. And shear stresses across the floodplain correlate to very low shear stresses as well. So the higher, slightly higher downstream water level, velocities within the same range, and the overall very low gradient across the system correspond to very low bed shear stresses and within the sort of the very low erosion risk category. So that review nonetheless has led us to think about what the implications of that backwater effect would be for the assessment, and I'll sort of talk through those as I get into the assessment. The review, though, also having identified that there's this backwater effect, we went back and revisited the frequency and duration of inundation when you experience this sort of 55,000 megalitre a day threshold downstream of the Walker Junction. And when we reviewed the river flows, the hydrological conditions, we found that under natural conditions, modelled natural conditions, inundation would have occurred or been expected to occur around to that threshold level around 8 times every 10 years, whereas the 30,000 megalitre a day Swan Hill event under natural conditions is only occurring around 3 times every 10 years. So there's actually, I guess, a redefinition of the baseline in terms of the frequency of inundation that would have been occurring under natural conditions when you take into consideration the Walker River effect. Under current modelled conditions, there's an increase in the frequency of inundation compared to what had previously been identified under current conditions, but there's still a gap between current and historical over the last 48 years. There's still a gap between the frequency of inundation as it currently occurs and the natural frequency of inundation. And it's that gap, I guess, that the VMFRP projects are aiming to address. So with the earlier analysis, there was a gap between existing and natural. And with the redefinition of the inundation thresholds, there's still a gap. The inundation happens more frequently, but there's still a gap to meet the preferred inundation frequency, and that's what the VMFRP projects are designed to address. And it was that gap that informed the revision to the project description and the update of the frequency of inundation. I will talk about the duration, or I'm happy to talk about the duration effects as we move through the presentation.
Before you move on from this slide, perhaps, Dr. Treball, can you just address a question which arose on the first day of the roundtable, which is basically, why have we no longer got a borough intermediate operational scenario?
I've got a slide in relation to that a little bit further on, so perhaps, if I may, I'll address that at that point in time.
Sure, thank you.
Yep, I've noted that though from the day one, and I'll talk to that. So moving on to the potential project effects, there's, as Mr. Oxley talked about, there's construction-related effects and operational effects. I'll talk through the construction effects first. They're relatively straightforward, I think. So construction has the potential to result in adverse effects to surface waters, including erosion and runoff from disturbed areas, resulting in turbidity and sedimentation of waterways. There's the risks of the exposure of contamination or acid sulfate soils during excavation and accidental spills, and Mr. Oxley talked about the potential for the discharge of groundwater to waterways if dewatering were to occur. So these things are all really well understood. They're generally applicable across all of the project areas, and they're applicable in general to the kinds of any sort of construction on a floodplain or on a river, the like that might be associated with building fishways that are frequently built along the river and along watercourses and anna branches of the Murray River. So these are common and well understood potential issues, and the delivery standards have been developed to manage and mitigate those potential construction adverse effects. This includes through the development of a construction environmental management plan. There's also a range of EDS around contaminated soils, acid sulfate soil management, groundwater management, and the like, that all collectively work to address and mitigate construction-related effects insofar as they might impact on surface waters. And so with the implementation of those relevant EDS, the residual adverse effects to surface water values are manageable, and we consider them to be low. So I'm not going to go into any more detail on those construction effects. I think they've been adequately dealt with. So I'll now talk about operational effects. I'll go through some of the effects in relation to erosion risk associated with various scenarios, and then I'll go through some of the water quality effects in relation to black water and salinity effects that have been identified through the process. So there's a number of different operating scenarios that I think you're aware of. There's an operating scenario called a seasonal fresh. That scenario is confined to flow or water within Burra Creek itself and doesn't involve any floodplain inundation. There are two water management areas, Burra North and Burra South, and they can be inundated in slightly different ways depending on the specific operations. Burra South can be inundated via high flows in the Murray River at the upstream end of the system at the B4 regulator, when flows get above about 22,000 megalitres a day in the river, irrespective of anything happening in the Warkall River. The flow can enter the upstream section of Burra Creek and flow down Burra Creek South. And pumping can also be used at that upstream location at lower river flows to generate an inundation of Burra South. Under sort of moderately higher flows at the top end, those flows can extend their way down to Burra North Burra North can also be inundated separately via pumping at the North Piambi Channel pump station. And so in that sense, the two areas can be somewhat managed independently. We've looked at the depths and velocities and shear stresses through the system in relation to the seasonal fresh. The seasonal fresh occurs when under circumstances when there's no backwater effect from the Walker River. And so the existing modelling, we believe, is appropriate for the assessment of effects of the seasonal fresh. We do see the potential for an increase in depth in Burra Creek with the addition of water for the seasonal fresh. And this is partly in response to the removal or modification of some block banks in the system that enable a bit more water to be sent down the creek, and that raises the depth. Bear in mind that this is all within the channel. It's not extending out onto the floodplain. The removal and the modification or operation of some existing structures also results in the potential for a slightly higher velocity through the system under certain circumstances. And that's actually not a bad thing. If you can create some velocity or some flow during a seasonal fresh, then it helps to flush out some organic material and the like that may have accumulated in the channel. And so this change in velocity is not considered to be detrimental. Nonetheless, despite the increase in velocity, there's no change in shear stress because the landscape out there is so flat. And this the graph or the map in particular shows the sort of the bed shear stress, which is I guess the measure of erosion risk along Burra Creek and during a seasonal fresh, and it's in that negligible category or low erosion risk category. So on that basis, sort of erosion effects associated with a seasonal fresh are considered to be low. So the other mode of operation is a maximum inundation operation. And I'll touch on the intermediate at the end. I'll go through the maximum first, and then I'll circle back to the intermediate. So the maximum inundation extent can be met under two circumstances. It can be met through unregulated flows with the regulators all open. And in the years that an unregulated flow doesn't result or there's not an unregulated flow sufficient to result in inundation of the system, then pumping can be used to fill the gap. And when we looked at the frequency and the duration of operation, we found that under sort of proposed basin plan conditions, an event to the equivalent of the maximum inundation extent would occur in those sort of 3 to 5 in every 10 years. And when it does occur under current conditions or proposed basin plan conditions, the duration of the unregulated event, when it does occur, is sufficient to meet the preferred duration of inundation. And so in that context, the unregulated event, when it occurs, provides for the preferred water regime. So in the years when the unregulated event doesn't occur, but it's desirable to have an inundation event to support vegetation, then the managed event would be wholly achieved by pumping. So they're the two operational scenarios. The intermediate scenario was for an intermediate extent of inundation. And when we looked at the frequency and duration of an equivalent event, with the consideration of the Walker backwater and the increase in the frequency of inundation that is occurring, that intermediate event is no longer required. So an inundation that's equivalent to that extent is happening at an appropriate frequency and duration anyway. So from a managed perspective, it was felt that the intermediate event could be removed as an operational scenario. It doesn't mean that you may, under an unregulated event, you could still get inundation to the equivalent of an intermediate scenario. But from an operational perspective, the intermediate scenario is not required to be managed or delivered in a managed way.
I'm just, we are going to hold our questions till the end, but I'm just going to jump in on this issue because we have had a little trouble getting our heads around why we don't need that borough intermediate scenario anymore. So are you saying as a result of the sort of updated understanding about the wall-cool effect, that's happening by itself?
Yes.
You don't need pumping, you don't need intervention from the project. That's happening at the frequency and the duration that you would have aimed for before you knew about the wall-cool effect.
That's right. Yeah.
Okay.
Yeah.
Thank you.
And that I think it is important to note, like I said earlier, that when the unregulated events do occur, they last for, generally speaking, the appropriate length of time to suit the vegetation, and it's only in those years when an unregulated event doesn't occur that pumping would be needed. So in that context, the sort of managed inundation is a pumped event, or the intervention is pumping in those years when inundation would be required but has otherwise not occurred because unregulated flows weren't sufficient.
Could I just jump?
Sorry,
no,
yes.
Sorry, could I just jump in just on the back of that question and just to ask, have you, in terms of the frequency duration of that event, have you prepared statistics in relation to that we'd be able to have a look at?
Yeah, those statistics, if I remember correctly, are presented in the addendum. I'll take that one on notice, Member Brisger, and double check rather than sort of launch into it
definitely,
now.
Yeah.
And if they're not there, then we certainly provided some advice to VMFRP that informed the update of the project description, and so that information will be available, and it can be sort of prepared into a tech note or taken on notice.
Yeah, it will be helpful to have those statistics.
Sure. Yep. So I guess notwithstanding the backwater effects of the wall-cool, we've looked at depths, velocities, and shear stresses under the conditions of an unregulated flow occurring with all of the infrastructure open and essentially allowing for unimpeded water movement across the landscape. I know that there's been some questioning about the use of box plots in the past. We've continued to use them because that was what we'd developed at the time of the original assessment. I note, though, that there's been some questioning about it, but nonetheless, the box plots show the distribution of depths at different points along Barra Creek itself, upstream and downstream of the various regulators and on the floodplain. And we see that there's no substantial difference in the depth distributions with the regulators open during an unregulated event. There's a slightly higher velocity downstream of the regulators, and we've seen this in past situations as well, where there's potential for there to be some velocity changes around the regulators during flow through those regulators, but where there's a very low overall gradients, that's not translating to shear stresses that are resulting in high erosion risks. Now, when we take into account the backwater effect of the wall-cool and the potentially higher downstream water level in the Murray River for a particular flow, then we'd expect to see that the velocity differential may actually be less than what was originally modelled. I'll move on to the pumped inundation. So during a pumped inundation event, the floodplain is filled from dry, or from mostly dry, and it's filled to a depth that's defined by the target inundation level of 58.7 metres. And so this is a depth map. It's showing depths in greater resolution than shown, which I think is useful. It demonstrates that the depth of inundation during this pumped event is, for the most part, really quite small, less than 0.4 metres across the majority of the floodplain. There's some slightly higher depths of inundation in Burra Creek itself and in some of these depressions and smaller flood runners. And so in terms of depth, it's defined by the target level of inundation for a pumped event. The effects that are associated with a pumped inundation occur, though, during the release of that water. So once the floodplain's been filled, the effects are during drawdown. And it's under this circumstance when there's potential for increased velocities along Burra Creek as the water that's on the floodplain is released back into Burra Creek and then down into the river. And the highest velocities are around and downstream of regulator B1. This occurs as water is released through that regulator into the lower Burra Creek and ultimately the Murray River. And because it's a pumped inundation event and it's occurring when there'd been no high unregulated flows, the discharge is occurring into the Murray River with a low tailwater level. And so the current modelling, or the original modelling, we felt was appropriate and sufficient to be able to identify the risk because there's no backwater effect occurring. We've got a low tailwater level in the Murray River, and so the effect is as modelled. And under this circumstance, there is an increase in velocity during the release of a pumped event. And this is upstream, sort of downstream and upstream of the B1 regulator, and more generally across the floodplain as well, as the water is shedding off the floodplain and flowing down Burra Creek when there's a low downstream tailwater level. And we can see the velocities in Burra Creek are mapped, getting some velocities up into the 0.4, 0.5 meters per second, which on the face of it sounds like a lot, but in reality, not really super high. But when you take into consideration the gradients, the shear stress that's associated with that velocity is still low. And a shear stress map showing all in blue the negligible shear stresses and the box plot showing the distribution of those shear stresses. So there are a couple of points where there's some slightly high shear stresses, but they're under the threshold that would represent anything other than a low level of effect. And this is with regulators fully open and the maximum volume of water flowing out of those regulators. And so even under that circumstance, the shear stresses are low and the erosion risk is low. There's the operational ability to control the rate at which water is released through the regulators, and in that scenario manage the downstream effect. And that's captured in the EDS around regulator operation. So we believe that the EDS is sufficient to require the regulators to be operated in a way that that minimises any of that downstream risk, Nonetheless, the downstream risk is in the low erosion risk category. So I'll now move on to the water quality effects. I'll try and move through these fairly quickly. So we've looked at dissolved oxygen. During an inundation event, there's potential for low dissolved oxygen conditions on the floodplain following inundation. These effects are restricted to the localised area within the floodplain and are unlikely to extend to the Murray River. We've modelled the dissolved oxygen effects using a Blackwater model that was provided by the Murray-Darling Basin Authority that had been parameterised for the VMFRP and all of the SDL or the SIDLAM projects that have been considered. And what we see when you have a pumped inundation event, there is a rapid decline in dissolved oxygen. This is this blue line. It stays low for quite some period of time. If there's the opportunity for through flow, after a period of time, the dissolved oxygen level starts to increase. Nonetheless, the through flow that's required to create that is fairly high, about 100 megalitres a day, which I understand is probably higher than the pump capacities for providing that through flow. So what we are seeing is the potential for low dissolved oxygen for a large part of the inundation event. When that water discharges to the Murray River, there's a very small effect within the river itself because the volume of water that's coming off the floodplain is relatively small compared to the passing flow in the river. And so with mixing and re-aeration, the effect is really quite small. And if you note on the scale here, we're talking in the 0.1s of a milligram per litre effect, which is not, from an ecological perspective, at all significant. The effect of the low DO in and of itself, that's dealt with in the aquatic ecology assessment insofar as there's potential for effects to aquatic biota that might be present on the floodplain. There are some things that can be done to minimise those potential effects, and that's managed through EDS SW2, the Surface Water Operations EDS, and that's around timing of inundation for late winter, early spring when temperature is lower. And then the rates of dissolved oxygen decline associated with the decomposition of organic material are lower, so while we're still seeing a DO decline, it's not as rapid as it would be compared to if we were inundating in summer. The effect would be more severe. And the overall increase in the frequency of inundation of the floodplain will result in an overall lowering of the standing material of organic the standing crop of organic material on the floodplain, so that over time we'd expect to see less and less severe dissolved oxygen events because the frequent inundation would be, in effect, removing the accumulated organic material that's on the floodplain. For salinity, we touched on the typographical error. I just wanted to point out the effect in terms of the salt load that Mr. Hoxley talked about. So the salt load of about 3 tonnes a day on average associated with managed inundation translates to around about a 3 milligram per litre increase in river salinity at a low river flow. Mr. Hoxley talked about the sort of the salt effects being accountable under the basin salinity management strategy. The river through here typically runs at around 150 milligrams per litre of salt of salinity concentration. 3 milligrams per litre in that context is really, really small. The kind of thresholds for effect are in the 300 to 500 or higher milligram per litre effects for water for irrigation purposes. From ecological effects, there can be as high as 800 or 1,000 milligrams per litre. So a 3 milligram per litre increase is really small in the context of potential effect. In terms of load, this graph shows the annual salt load in the Murray River at Swan Hill. Each of the dots represents a year. We've got salt load on the y-axis and the total annual flow on the x-axis, and you can see that in years with very large annual flows, we get a very high salt load. That's as you'd expect. The greater the volume that's heading down the river, the more the water is carrying salt. So in flood years like 2011, 2016, I haven't got 2022 or 2023 on this graph, but I suspect they'd be out here somewhere. The salt load that's being contributed by the Burra, by managed inundation at the Burra site, is in the red line that doesn't even get off the bottom of the axis. So it's really small in comparison to the actual salt load that's heading down the river anyway. In terms of nutrients and algal blooms, there's a small increase in the net load of nitrogen and phosphorus to the Murray River in return flows. It's less than 0.1% of the total river load, and we believe that to be insignificant. There's obviously with inundation, natural or otherwise, there's risks of algal blooms where water might be standing on the floodplain. The timing of inundation is important to try and avoid periods when we might see higher algal growth. Excuse me, I'm just going to drop my blind because the sun's shining in my eye. So there's a lower risk of algal blooms developing if inundation is occurring in winter and early spring. Temperatures are lower, the light intensity and the light duration are not as high. So those things are captured in EDS SW2. Monitoring, we've got a monitoring program that's been recommended. This would be used to evaluate watering outcomes and adaptively manage watering events and inform future water planning and operations. The program describes the requirements for the various indicators, monitoring locations and monitoring frequency. I won't go into detail other than to point out in response to a question to Mr. Hoxley around salinity monitoring. Within the monitoring recommendations, there's recommendations for sites in the Murray River upstream and downstream of discharge locations during a managed event, and that EC or salinity would be one of the variables to be monitored during that time. And in that context, it can be examined what the effect of any salt associated with a discharge would be to the river. More broadly, in terms of longer term, the return of salt to the Murray River, there's routine monitoring that's occurring at Swan Hill and at downstream of Walkle Junction. And we believe that in the longer term, those sites would be appropriate for assessing any kind of longer term return of salt load back to the river.
Dr. Treadwell, on that slide, you talk about EDS as SW2 and SW3. In talking further about the monitoring and that specific question of monitoring in the Murray River and upstream and downstream of inflows, are you referring to monitoring requirement SW2, which relates to assessing the effect of environmental watering on surface water quality on the floodplain and within the Murray River?
Yes. Yeah.
Thanks. I won't share it on the screen now, but for the committee's benefit, it's on page 17 of the day one EDS as a monitoring requirements, which is table document B21.
Cumulative effects considered in the context of delivering environmental water to multiple sites. We've rated this as low. The sites are far enough apart such that if there were an effect on the Murray River, it's rapidly mitigated through dilution, pretty much at the point of discharge. And so there's, by the time you get down to the next site, there's been sufficient re-aeration in the river and the like, and the modelling has demonstrated that any effect is really very localised to the point of discharge. The only potential cumulative effect, I guess, is in relation to salt loads. Salt is non-conservative. It builds up, and so in that context, it continues to build up as you travel down the river. There is a cumulative increase in salinity at the South Australian border. It was documented in the table that was talked about earlier. Despite that cumulative increase, it's still relatively small in the context of the total salt loads in the river. And as Mr. Hoxley talked to, it's accountable under the Basin Salinity Management Strategy.
I'm just mindful of the time, Dr. Treadwell. Our directions did say 30-minute presentations, and we've been going for 45.
Oh gosh, it's really difficult because I've got so much to get through with there being multiple kind of elements to the surface water effects. Yeah. No,
we appreciate that. There is a lot to get through, but we also have quite a lot of questions for you. So if I can just ask you to move through the rest of your slides relatively quickly just hit the sort of key points.
I'll hit the key points. Yeah.
Thank you.
Thank you, Member Carlisle. Summary of submissions. I will be able to move through these pretty quickly because I think I've pretty much addressed, hopefully I've addressed them through the presentation. So there were concerns that managed inundation changes the way water moves across the floodplain, that holding or ponding water on the floodplain doesn't replicate a natural event, that some areas of floodplain may miss out. There was also questioning or concerns about the modelling, water planning and delivery approaches. Blackwater, I've talked about. Monitoring overall effects on Ramsar sites and the effectiveness of EDS. So I'll try and whiz through these really quickly. The effects in terms of the infrastructure. The infrastructure has been designed to enable unregulated flows to continue to pass across the floodplain when they do occur. At Burra Creek, as we've heard, during an unregulated event, all the regulators would remain open and the flow paths, generally speaking, would be as natural. Suffice to say, there are containment banks, but they've got spillways on them to enable water to be able to spill over those containment banks during higher flows. And so in that context, we feel that the sort of the hydraulic conditions during unregulated events are not going to be substantially impacted. I won't go into any detail on the modelling or the information used to inform the assessment. I think the Minister acknowledged that the modelling or the information available at the time and the approaches were considered to be suitable and the best available flow at the time. So I won't go into, excuse me, any more detail on that. Similarly with the assessments of climate change, I think that was considered to be appropriate. The water planning and delivery approaches have been well documented, and I think they've been considered appropriate. There's some questions in relation to site management and observations related to the use of temporary structures. This is more generic rather than specifically to Burra, but the projects in general aim to remove the need for temporary work structures, and that they would be replaced with the more permanent structures or operated in a different way to enable the projects to proceed. And those operations would be guided by site-specific operating plans that would manage those structures and those in that context. And the Mallee CMA is responsible for developing the operating plan and for implementing it in consultation with stakeholders, including private landholders where they might be affected. I've talked about the Blackwater effects, and so they were raised in submissions, but I think they've been adequately addressed. In terms of Ramsar site effects, the Burra Creek is not a Ramsar site. The nearest Ramsar site is about 200 kilometres downstream at Hatta Colquhoun Lakes, and there's no construction in a Ramsar site, and we've demonstrated that we believe there's no sort of long duration, long distance downstream effects. And so in that context, the Burra Creek project in and of itself doesn't represent a risk to Ramsar sites. We've noted the only additional submission subsequent to the addendum that was relevant for Burra was the EPA submission. We've noted that. Environmental delivery standards, residual effects and adaptive management. As we've heard, the EDS were developed with reference to factors that that may need to address particular effects. We've looked at scientific literature, evidence from research within the MDBA and outcomes of effectiveness of past management measures and used that to inform the development of EDS. I've talked about the construction EDS. The residual effects for construction hence are considered low with the application of those EDS. The environmental delivery standards for operation include measures around factoring of seasonal implications for watering, the provision of through flow where possible, managing drawdown rates to manage those downstream erosion effects, and the development and testing of a native fish exit strategy and carp management strategy, which I think Mr. Benier will talk about in more detail when he gives his evidence. There are a range of other EDS referred to in the specialist assessment that are also relevant to the management of surface water in relation to contamination, like contaminated land, soils and geology and the like, and they're all documented in the specialist assessment. And on the basis of all of that, we believe that the effects of operation are generally low and where there are effects that have been identified, they can be effectively managed through the application of the EDS. Suffice to say that obviously monitoring is required, and that monitoring is implemented through an adaptive management framework, and that should be used to inform decisions both during operation and for future operations around how the system is operated. And that's the end of my presentation. Sorry for taking a bit longer than anticipated.
Okay, again, I'll invite parties who have questions for Dr. Treadwell to turn their cameras on, but what we'll do is we'll run this in the same way that we ran it for Mr. Hoxley. So the committee will put its questions first. We've attempted to block our questions into sort of issues. And I've got to say that member Briscoe is going to be doing the heavy lifting on asking questions of you this afternoon. Sandra, what we might aim to do is get through the first sort of issue or two, and then around 1 o'clock, or, you know, when we get to a natural pause point, we'll break for lunch.
That's right. Yeah. Did you want to start with the broader questions, or did you want to start with more specific ones?
I think we maybe deal with the broader questions before lunch, and then we can get into the nitty-gritty after lunch.
So did you want me to lead those, or did you want to start?
If you're happy to, or my notes are all jumbled up with your questions and my questions now. So
okay, no, I can lead that. So I might just okay, so we've got some questions, I guess, and this is maybe a little bit jumbled up, but just with the containment banks in the first one's about how the water moves in and out of the Burra Creek floodplain, and you say that the containment banks are not intended to stop the movement of water. They're supposed to be, I guess, movement of water through the regulators and so forth. Given the effect of the backwater from Lycul, how confident are you that the containment banks aren't affecting the inflow of water to the floodplain or the outflow of water from the floodplain?
So with the, as I understand it, with the backwater effect, it extends up Burra Creek, and so you've got water entering the floodplain from Burra Creek, but also at excuse me, locations along the Murray River bank as well. And so the kind of, I guess, cumulative effect of that is water entering the floodplain from multiple locations. The containment banks have got low overflow points on them. So as the river gets higher and higher, then water would also spill over those containment banks from either direction, depending on the relative heights of that the river and water level in the floodplain.
I might just sort of zoom in a little bit more specifically on some of the modelling and explore that in a bit more detail, and we might sort of come back to that at the end. I guess I'll get down to, first of all, the first question about the modelling is about the RIC hydraulic model, which you've referred to. And I just wanted to understand, I guess, what degree of access you had to that model and how you used it in comparing the work that you've done with the Boreham model with what the RIC model was showing.
Yes, so the modelers requested the output files from the RIC model, and we were granted those files, and they've used those output files to post-process, I guess, some of those hydraulic statistics that were then able to be compared with the similar statistics that were produced from the original modelling.
Okay, so with the RIC model, was that a similar resolution or a coarser spatial and vertical resolution than the Boreham model?
I'd have to take the specific details of that on notice, but I think, if I recall, there's a table in the addendum that compares the two modelling approaches, but I'll take that one on question because I don't want to misrepresent one or other of the models.
Yeah, I just wanted to make sure we understand that.
I might just jump in with one of the sort of more general high-level questions there. We understand, and you've explained during your presentation, why the Borough Intermediate scenario is no longer regarded as needed. We were just wanting to explore whether, so obviously most of the inundation and most of the scenarios are focused on the Borough North water management area.
Yep.
There is the Borough South management area where there'll still be some seasonal fresh where you're aiming to fill up the channel. Is there no residual role for that intermediate operating scenario in the Borough South management area where it may not be experiencing the wall-call effect?
No, my understanding for Borough South is that it's purely for the seasonal fresh. There's no floodplain inundation proposed for Borough South. And so in that context, the intermediate scenario doesn't apply to Borough South.
Okay, got you. Thank you.
Yeah. I'll just jump back to the RIC model and the post-processed, the output files that you then apply to the post-processor for. What kind of output files were specified? Were they in the form of depth and velocity and that kind of thing, hydraulic parameters, and were they for particular flows?
Again, I'm sorry, Member Briscoe, I'll have to take that one on notice. Given that we were able to compare depth, velocities and shear stresses with using the RRC model outputs, I'm assuming that appropriate data was provided to enable those metrics to be calculated.
Yeah, I'm just interested in terms of whether there were particular flows, whether it was just at particular flow levels, whether it was across a range of flows, a broader range of flows.
The RRC modelling, as I understand it, is available for a range of flows, about 10,000 megalitre a day increments. And so I'm assuming that we would have received it for all of those flows.
Yeah.
The only flow threshold from the RRC model that results in inundation of Borough Creek is that 55,900 model run. And it's, I mean, if I may, the RRC model is based on what it relates to constraints relaxation projects. And they modelled a range of flow thresholds at various points along the Murray River that could be that would occur depending on the level of constraint relaxation that you could achieve downstream of Lake Hume in particular. And so the 55,900 threshold for Warcool corresponds to a constraints relaxation that enables something like in the order of 50,000 megalitres a day to be passed through the Upper Murray River at Tocumwal or the like. And so the downstream flow thresholds are related to the constraint relaxations that were modelled at the upstream extent, and they did it for a range of levels, not a continuous flow series.
Yeah, and so in terms of the modelling, I understand the Burra Creek model is used at steady state, so the models just run at steady state at particular flow levels.
Yeah.
Is that the case for the RRC as well?
I'm not sure about that. Again, I'd have to take that one on notice if you're wanting more detail around that.
It would just be helpful to understand what's being compared, the attributes of the model. And my next questions relate to a figure you got on slide 5.
Slide 5. Would you like me to share that?
Yes, please, because I've got quite a few questions about that, because it used to be a fairly important comparison between the two models. And I'm particularly interested in the figure you've got in the right-hand corner. So is it possible to zoom in on that?
I will. Oh, hang on. Bear with me. I'd rather do this. Is that sufficient size?
Yeah, that's good. Now we can have a look at that.
Yep.
Okay, and somewhere I think it's in the addendum you made the statement, or you made a statement to say that at flows of the Murray River at Swan Hill less than 25,000 megalitres a day and less than 45,000 megalitres a day downstream of Warcool Junction, there is no backwater effect. I'm just wondering how you established that.
So a couple of ways. In this particular graph, the grey line is 47,000 at downstream Warcool Junction, and it's the water level elevation is below the maximum inundation extent at Burra, so we're not getting water up to the managed inundation extent. And if you go down to 40,000 megalitres a day, the water level gradient across the section of the Burra floodplain that we're talking about is quite some distance below the managed inundation extent. So there was that element of the reconnecting river country model. What we also did, and it's presented in the addendum, was to look back over sequences of satellite imagery and correlated that with river flows at the times that the satellite imagery was undertaken. And I think in the addendum there's a graph of river flow at Warcool Junction and at downstream Swan Hill, and it shows whether from the satellite imagery the Burra floodplain was fully inundated, partly inundated, or not inundated at all. And it was through that process that we worked out that threshold for when inundation commences and when inundation achieves the maximum inundation extent. We also had some water levels extracted from satellite imagery at the edges of the inundation extents, and we used that to further try and define exactly what, or the range at which that backwater effect starts to have an effect.
Okay, I guess I'll just refocus that question, I guess, in relation to this graph and in terms of the water surface profile on the Murray River. Then you're saying you weren't interested in backwater effects that were lower than something close to the full supply level of the managed inundation event, and so you didn't look at it. So I guess one of the things that occurred to me looking at that graph is you've really got two series of water surface profiles, one lot out of the RRC model and one set out of the Borough model. And I guess, did you look at the same flows in the RRC model and the Borough model? So I understand from the RRC website that their model goes down to 15,000 megs a day Yarrawonga Weir, which is 19,000 at Swan Hill and 26,000 at Waikul Junction. So I was just wondering how that would, for example, compare with those water surface profiles that you have based on the Swan Hill data of the Borough model.
Yeah, so there are, like you say, lower flows for some of those lower thresholds, and they would, I imagine, if you were to put these on this graph, they would be even lower down on the graph down here. I guess we were mostly interested in what happens at around the managed inundation level in terms of the effects of managed inundation and how that would compare to what happens at the moment.
Yeah. Do you think that would be a useful exercise to make that comparison?
Of even lower thresholds?
Yeah.
I mean, we can make that comparison. I'm not sure that once everything's sort of down in the main Murray Channel, I don't think we'd see any effect of it. But if you're asking, I guess, at what is the downstream Waikul flow that initiates inundation, then it's around that 45 from the, I guess, the forensic, if you like, looking at satellite imagery and the like, it's around that sort of 45 to 50,000 megalitre a day effect. And when the water level is lower than that, when the flow level is lower than that, we don't see inundation of the Borough floodplain.
Right, because on Borough Creek, I guess you've got, and I'm assuming that level, the black line you've got across the graph there is the full supply level or the operating level at the maximum inundation area, and the B1 regulator, I think, is 3 metres high. So flows from backwater or otherwise will be coming into Borough Creek at a depth of something about 3 metres below that. Is that correct?
That would be right. So if you're in that sense, you're at 1, 2, 3. So you're, I see what you mean. Okay, so you're wondering at flows down at this kind of level down here, 3 metres down, are we seeing water coming in? Yeah. Okay. Well, what we do see at Borough is water can start extending up into the bottom end of Borough Creek when the flow at Swan Hill is at that 20,000 megalitre a day range, and so that is consistent with flow entering at the bottom end at about that range. What we tend to see with the Waikul River is that during the sort of normal run of river flow, there's very little flow coming out of the Waikul River. And so the contribution that it makes on top of flow coming down from Swan Hill is really quite small. It's only during the larger flood events that the inflow from the Waikul River starts to add substantially to the Murray River flow, and it's because during a big event further upstream, water during a flood in the Murray River escapes the Murray River channel and travels into New South Wales through a number of distributary channels, the sort of the Edward system at Barmer, the Kundrik Paracuta system further downstream, and they travel north and then captured by the Edward Waikul system and then rejoin the Murray River further down at the Waikul Junction. And so when there's not a large flood, we don't have that really large contribution coming out of the Waikul and the flow at Swan Hill and the flow at downstream of Walkall is very similar.
Yeah.
And so at those lower flows, there's not this sort of contribution from the Walkall as such.
Yeah. So going back to that and understanding that process, from the viewpoint of operations and adaptive management, would it be useful to understand to basically understand the water surface profile as it is, with including that backwater effect even at those lower flows?
Yeah, sure. For the sake of completeness, it would be, yeah, I acknowledge that. And
the other, I guess one more question about this graph. I'm conscious that we're sort of getting close to the scheduled lunch break. But on the left-hand side of the graph, we've got the Swan Hill water surface profiles, and a couple of them for the two higher events, which I can't read because I've got people's faces there, but I'll just get rid of that. The 35,000 and the 30,000, they're quite a bit higher up elevation-wise than what the water surface profiles are in the RRC model. Which model do you think is more accurate?
Yeah, look, can I take that one on notice to try and talk to the hydraulic modelers to understand that difference up there? Yeah.
Yeah, sure, that would be helpful. And I guess the reason I'm asking that question is that I guess that area is relevant to the Borough South part of the water management area and breakouts and so forth. And I guess where the water level there, so where the water surface there is, would depend as to how frequently the breakouts occur. So that would be good to get some advice on that. And I'm just scrolling down there. My next question is about another diagram. And I'm just wondering, in the colours, is this a good time to break for lunch, or should we keep on going?
I think if we've still got, is it about the RC model?
It's about the rating curve at the mouth of Borough Creek. So it's to do with the modelling and the flow levels and the Whitehall effect.
But it sounds like it's a sort of a different aspect. So I think
that's
now
right.
would be a good time to break for lunch. So we'll break and resume at 2 p.m. Okay, I'll hand back over to Member Brisger to resume questions on behalf of the committee.
Thank you. And Dr. Treadwell, I'd ask you to turn to the revised specialist assessment report, and there's a figure 3.4, which is a rating curve. I'd like to discuss that. It would be helpful if we could screen share that.
Yes, 3.4. Yeah, let me see if I can do that.
That's great, thank you.
Yep.
Yes, I just want to understand how that rating curve was developed, and I guess first of all, about the measurement of the spot heights at the Warcool Junction or downstream end of Barrow Creek. When were they measured? Were they measured all during a single flood event, or are they peaks of different flood events?
They were different flood events. So with the benefit of now being able to access historical satellite imagery from Sentinel, we were able to go back through those images and identify times when there was observed inundation of the floodplain, and the GIS specialists were able to extract from those images spot heights, and we correlated those with flow downstream of the Warcool Junction, and through that process derived that rating curve.
Okay, so with that extraction from Sentinel, are they fairly accurate, the spot heights?
We did it for quite a number of locations, as many as we could, so that we could try and get an average.
And the vertical resolution on those, is that a fairly tight vertical resolution?
Sorry, in terms of the white.
No, in terms of the spot height, if you're extracting the spot heights or elevations off the Sentinel imagery, I'm just wondering how accurate those heights are off the images.
Yeah, look, there's definitely going to be some uncertainty in that. We chose locations where the ground elevation was flattest, I guess, rather than on vertical riverbanks and the like, so that any variation in height would be more easily seen in terms of an inundation extent. Obviously, if you're trying to pick heights off a more vertical bank, then that's going to be much more difficult to accurately select. So they were from sections of the floodplain that were flat, where you'd expect to see a larger change in inundation for a smaller elevation change.
I see. So is there a sort of known vertical resolution accuracy for the Sentinel imagery, or does it vary?
Yeah, look, I'm not sure about that. I'd have to talk to the GIS, find out from the GIS people as to what the Sentinel elevation resolution is.
That will be helpful to know, just as in with the LiDAR and other sources of information, the environmental report specifies a vertical resolution, or certainly the Jacobs report specifies vertical resolution. It would be useful to know that too. And so I guess the next question I had noted is probably not relevant as to whether they're measured on a rising or falling limb. If they're at the peak, they're at the peak, so then it's not affected by rising and falling processes. Is that correct?
They were rising or the peak. We didn't select them on the falling limb.
Okay. And with the blue dots on that same graph, from the caption there, I understand they're from the Barrow Creek hydraulic model. Is that the Jacobs 2017 model?
That's right.
Yeah. Has that been calibrated at all?
At the time, my understanding is that that model was not calibrated.
Okay, and subsequently?
No new modelling has been done with those models as part of the assessment. It's only been the use of the outputs of that model.
Okay, so it's taken at face value.
Yeah.
Okay, now with that rating curve, and this is just trying to understand how to read it if for a set of flow conditions specified at Swan Hill and Waikul. So with the flows in the river today, we've got 23,000 megalitres at Swan Hill and just over, so 50,400 megalitres a day at Waikul. How would you interpret, from those figures, what would you infer from that rating curve? What would you interpret from that rating curve about current conditions?
So the way we've interpreted this is that after a certain point, for the location of Burra, the rating curve for Swan Hill becomes, if you like, sort of superseded by the rating curve that you get from Burra once the backwater starts to take effect. And so the flow at Swan Hill is less material to the water level at Burra. And we believe that happens at around that sort of 25,000 megalitre a day mark at Swan Hill, if you've also got flow above about 40,000 megalitres a day at Burra.
Yeah.
So if you had no inflow from Burra, inflow from the Waikul, then the rating curve at Swan Hill or the rating curve derived from Swan Hill would continue to apply up to the point that you start to get the inflow from the Waikul that overrides or starts to create that backwater effect.
So in terms of the figures I quoted you, with those figures, would you then infer that there's extensive flooding on the Burra floodplain at a Waikul flow of 50,500?
There's certainly flooding. The actual extent, when you look back through the satellite imagery, the extent does slightly vary from different floods. Not every single flood at 50,000 appears to inundate exactly the same area, and so hence the sort of a line of best fit on this particular curve to find that spot that, for the most part, the flow at Burra, as the flow downstream of Waikul that equates to the managed inundation extent, but there's no doubt that there's inundation occurring at Burra at a lower Waikul flow. It's just not up to the MIA level. And so at the moment, at 50,400, there's certainly inundation at Burra. It's a bit difficult to tell exactly whether it's at the MIA level at the moment or not from the imagery. It looks pretty similar to what you might expect for a managed inundation extent looking at the imagery, but it's a bit difficult to tell from the actual satellite imagery.
Thank you for that. I guess those numbers are sort of fairly keen interest to us over the last couple of days, because we were trying to make a decision about whether to go and do the site inspection or postpone it based on the extent of flooding and likelihood of getting access to the project area. So it sounds like by postponing we may have made the right call.
Well, look, I don't know what the condition of the tracks are like out there. I mean, there's been no rain in the district as far as I'm aware. This is a sort of a flood that's been generated from upstream, and so access tracks may well be passable. I think it would be interesting to get out and have a look and see what it looks like during inundation, and then you'd get an appreciation of the relative levels in the Murray and on the floodplain and the like. There are spots that you can see the sort of parts of the managed inundation area. But I guess you'd need advice from the CMA and Parks Vic as to whether the floodplain's actually accessible. But the water's up there, and it'll be up there for a little bit longer, I'm sure. It takes a little while for everything to sort of relax and calm down out there once a peak goes through.
Thank you. In terms of, I guess you say that for a particular borough, or not, for a particular Waikul junction flow, there's a bit of variation in terms of extent of inundation that may be related to the Swan Hill flow. And I guess I'm asking, in terms of this rating curve, would it provide more I guess, more detailed, more specific information if the rating curve were drawn in the form of a rating curve for a site with variable backwater, as the hydrographers do, where they have, I guess, for a given Swan Hill flow, a range of different possible flood depths depending on what the downstream of Waikul flow is. So you could read off, say, for a Swan Hill flow of, say, 25,000 megalitres a day, what the elevation might be if the flow downstream of Waikul were 50,000 or 55,000 or 60,000 in those categories. Was that approach considered at all?
Not that I'm aware of, but I understand what you're saying, and I guess that kind of curve could possibly be constructed.
Yeah, I'm just wondering if that might be something that would be useful for adaptive management or operation.
I mean, I guess it could potentially be useful for trying to further nuance, I guess, the frequency and duration of inundation under a range of different unregulated flow scenarios.
Mm-hmm. Yeah, and in terms of the scenario descriptions, currently the scenario descriptions, the seasonal fresh one only refers to the Swan Hill flow, and the maximum one only refers to the downstream of Waikul flows. With that approach of the variable backwater curve, would it be appropriate to describe the scenarios with reference to both sites? So for the seasonal fresh one, basically no assumption, or could be about the downstream of Waikul, or could even be zero downstream of Waikul. It's irrelevant. Whereas for the other one, there may be some predisposing condition downstream of Waikul to create that flow that's necessary, as well as the Swan Hill flow.
So for the seasonal fresh, the kind of flows that generate the movement of water into Barra Creek, but without inundation of the floodplain, we felt that happens at a flow downstream of Waikul below the sort of, well, if you were to use this graph as an example, below the 40,000 to 45,000 mark, which is where water can start to come in.
Yeah.
And so for the seasonal fresh, the Swan Hill rating curve, for the most part, makes the most sense, or as represents the best representation, I suppose, of the likely frequency of inundation. And for the maximum inundation extent, we felt that the downstream of Waikul represents the most representative gauge, because the flow required at Swan Hill to achieve inundation is in that 30 to 35,000 megalitre a day range, and it very rarely occurs in the record when you look back through the record. And whenever it does occur, the flow downstream of Waikul is, on those instances, has exceeded that sort of inundation threshold of the 50 to 55,000. And I think I can probably, rather than clumsily trying to describe that, if I go down, maybe it's up. I'm not sure if I had a graph in here to describe that. No, perhaps not. No, there it is. There is one in there. So this graph here is sort of talking to that effect, where we've got flow at Swan Hill on the y-axis and downstream of the Walker Junction on the x-axis, and these points in the orange represent circumstances where there was no observable inundation of the floodplain from the satellite imagery, and where we've seen some partial inundation and where we've seen a larger extent, sort of full inundation of the floodplain. And so the occasions when flow gets above about 25,000 at Swan Hill, it's invariably above 40,000, and there's even larger events at 30 and 35,000 at Swan Hill. It's at, much higher, again above the sort of threshold of what we've defined as being that level that gives you the maximum inundation extent.
Yeah, and to clarify, all of these levels, all these points here, they're flood peaks or close to the peak levels.
Yeah,
again.
yeah.
So
yeah,
sort of
as close to the peak as possible, or on the rising limb. We didn't use downstream, falling limb, because obviously the river falls faster, or has the potential to fall faster than the water drains off the floodplain. Yep,
understand. So, so with all of this, so these rating curves are based on the peaks, and then the two hydraulic models. So the hydraulic model, the Jacobs model, that's based on steady state.
Yeah. Oh, I've lost. I can't hear you, Member Briscoe.
Yep. Something's happened to your audio, Member Briscoe.
You can't hear me?
Oh, now we can.
No, you can.
That was
There's a
strange.
screeching cockatoo flew past just before, so unless it muted itself on that. So I was just going to just clarifying and confirming, I guess, the Dr. Treadwell, that the information that we have in the environment report and the addendum about floods and ratings and so forth is based on either peak flows or steady state at a particular flow. We're not sure about the RRC model, but we're clarifying that.
Yep.
My next questions may go beyond probably do go beyond what's modelled, but I think they're important questions, and that's actually how the floodplains operate when the inundation occurs. And I wanted to have a look at some diagrams that are in the story map. So I'm not sure, Dr. Treadwell, whether you've seen those or have access to those. So they're show the directions of water movement.
Okay, I don't know whether Mr. Forrester, are they something you can find?
They are. It'll take me a few minutes.
Yeah, let's just
I'll move on
to let let's just pause to let Mr. Forrester, because it seems to go in the flow of the questions. And I think it would be really helpful to have a visual to talk through these questions.
I hope that's now there. I've got the project context and project description story maps open.
Thank you. The one I'm looking for is Burra Creek water movement. And the seasonal fresh operating scenario. And it looks like it's taking a while for the arrows to load.
Yeah.
They're loading. And I guess the first question, I guess, Dr. Treadwell, I understand you would have seen these maps before.
Yes.
My input to those, yes. Are they based on your modelling or understanding of the hydraulics, or were they done by someone else?
Those maps have been prepared by someone else.
Okay. So for the seasonal fresh operating scenario, it's got directions of flow where the water would enter and move through the floodplain. Is that consistent with your understanding of how the inundation process operates?
So I guess there's two mechanisms that as the water level rises, it comes in at the bottom end, and as it rises further, it can then also spill in at the top end and work its way down the system. And so you've got this not competing, you've got inundation from both ends, depending on the ultimate height that the river gets to.
Yeah. So this figure is showing for the seasonal fresh. It's predominantly coming in from the northern or downstream end.
Yeah,
that'd be correct.
And then if pumping was to be used to generate that event or to augment that event, then it would come in at the that North Piambi channel hard stand.
Yeah. And so that's at the upstream end it would come in.
Yes.
And so in terms of the Jacobs model, is that model of hydraulic model, is that the assumption they make there of the water moving in from the bottom end and coming up?
My understanding of the model is that, yes, it will demonstrate both of that, coming in from the bottom end and also coming in from the top end when the flow gets a little bit higher at the top end.
If we go down to the next figure, Mr. Forrester, which is the maximum operating scenario. And we might just have to wait a couple of minutes for the arrows to load. I guess, Dr. Treadwell, I had a similar question, but I'll give you a chance. I'll give a chance for the arrows to load for you to have a look at them.
I'm finding it a bit hard, even at that slightly blown up scale, to see where the arrowheads are. I think it's clear, but are you able to just make that a little bit bigger, Mr. Forrester, so we can see the arrowheads a bit more clearly?
I can, but I expect it'll mean we have to look at one of the WMAs at a time.
Yeah. Let's do that. Let's look at the southern one first. That might be the simpler.
They're not very pointy arrows.
No, they seem to lose their pointiness as you enlarge them too.
And for what it's worth, the direction of flow is from the bottom of the page to the top of the page.
Yeah. And is that in accordance with your understanding from the hydraulic work that you've done?
Yeah, so as the river rises at the upstream end and exceeds the commence to spill levels at the upstream end of Burra Creek South, then it spills into the creek and it runs down the channel, or it can be pumped in at that B4 pump.
Yeah, and so the level at which it spills in depends on the water level on the Murray River, is that correct?
Yes, yeah.
And so in terms of how that's represented in the hydraulic model, that will depend on how accurately that level is represented in the hydraulic model.
Yes, it would.
Yeah, so I guess my question or concern is, having looked at those water surface profiles on that first slide we looked at, which had quite a big discrepancy between the RRC model and the Burra model, just a question of whether those two different interpretations of the water surface profile will lead to quite different interpretations of how frequently this inundation occurs.
Yeah, look, I understand the point of the question. I would have to defer that to the hydraulic modelers to ask them for an opinion on that.
That would be helpful.
If that's okay. I'm
sure.
not trying to be evasive or anything like that. It's,
No.
you know.
Yeah, no, I'm not trying to sort of put you on a spot to answer questions you don't feel that you can answer, but they're important questions that we need to understand.
Absolutely, I understand that, and you know, I have had to rely on the hydraulic modelers for a lot of for the content and the effect, and yeah, I don't want to answer for them those sorts of, you know, valid but detailed technical questions. I really would like to go back to them and ask them, because I don't want to misrepresent or give you a misrepresented answer. Yeah. No,
totally. So I'm very happy to put those as questions on notice, but I'm asking these questions because they are pieces of information.
No, absolutely.
Important to us to understand what we need to understand. So that's what I'm asking. So we if we move down to the Borough North area, I think the situation is a little bit more complicated. And we think we do need to, hopefully the arrows show up a bit more clearly in that. I'm glad I'm not the only person who's had this thing load very slowly when they've tried to look at it on their computer. But basically what I saw when I had it open on my screen, and I think the arrowheads are less pointy than they were when I looked at it on my computer, is basically the water coming in from the northern end or the downstream end and then sort of working its way upstream, swelling around, and the predominant entry being from the downstream end, working its way around and then coming out again.
So water coming down from the top end, and water coming in from the bottom end of the level. Okay,
and it appears from how the arrows go that a lot of the water, that it's an important source of water, is from the bottom end, or from the bottom, as in the northern end.
Yes, I would say that.
The length of the arrows doesn't indicate a sort of proportional volume of water that's coming from one direction or the other, does it?
I don't know. I don't think so. I thought, well, the version of the map I've got, which is table document 26, I think, has the arrows a little clearer and bigger, but I think they're all the same length and the same thickness. I'd have to check with whomever prepared the map, but I don't believe they represent relative volumes.
Yeah, okay.
Okay, now if we look at this map, over on the north, on the northeast, there's the main containment bank, or the first containment bank, with was B1 regulator and a couple of spillways in the containment bank. If that containment bank weren't there, would the water come, would that be an important inflow area as well into the floodplain? And it may be a question you can't answer because the hydraulic models mightn't have been done in a way that can inform that.
Yeah, look, I'm not sure. My understanding is the containment banks would have been identified, or the locations of them would have been identified with appropriate consideration of where water comes in and out of. But that's probably a question for the CMA and in the development of the project in terms of the location of containment banks.
Yeah, because I guess one of the questions, also to explain the line of thinking along this, is that the project, I understand, was designed with input from the borough model, as in the Jacobs model, which didn't have the Waikul backwater effect in it, and so it was less obvious how important that the inflows from downstream were into this area. And then in the design of the containment banks, with that information, it would have been quite reasonable to not expect much inflow to come from the northern end, or as much come from the northern end at such high levels. And therefore, it's possible that containment banks may have been designed at a level that could actually block what would be an important inflow area for water coming in from that backwater. And so I guess my question is, it may be something that you can't answer. It might be a question that you sort of say, well, it's an important question, but our models don't allow us to do that. But
Yeah,
I guess the question is, is that affecting the interaction?
Yeah, I see where you're coming from, and I think yeah, you're right, and you've essentially answered the question. I would need to double check that as well. Yeah, but I understand
it would be good to understand the modelers if they've got any tools that they've used or could use that could examine that or assess that. Because you'd be aware and they'd be aware of modelling where you can actually rather than run a steady state, you actually run through an event and watch the waters inundate the area and then dry up again with the stepping through the hydrograph. And it would seem to me that something like that might be, with the Burra backwater effect included, might be a very useful tool for understanding what's actually going on in relation to those containment banks and the water coming in at that northern end of the floodplain. And so I'm not sure whether the RRC model's got the capability to run an event in that way to examine that, or whether it would need to be a whole new model.
Yeah, I'm not sure. The thing I do know about the RRC model, obviously, is that it doesn't include any of the project proposed infrastructure.
Yeah.
But it might be possible to do what you're suggesting in terms of at least identifying those overbank locations.
Yeah, even to understand how it operates without the infrastructure.
Yep.
Be handy. Okay, now with the Waikul, with this effect of the Waikul backwater, does the inflow from the Waikul, this might be another question that's might need to go back to the modelers, but does water just come down the Waikul and keep on going downstream towards the downstream end of the Murray, or does it actually curl back, and does it actually backflow as far up as Burra Creek and flow back into here like a reverse eddy, or is it too big a distance?
It's quite a long distance. This is my speculation, I guess, if I can speculate, is that you've got, rather than flow coming backwards necessarily, it's building up as a result of the flow that's continuing to come down from the Murray itself, and that combination of a large inflow from the Waikul, essentially creating a barrier, I suppose, that that then fills up on the upstream side of that as the Swan Hill flow comes down. The extent to which the river actually flows backwards, I don't know. I mean, I do know that there are examples of that when the Goulburn, at the junction between the Murray and the Goulburn, and sometimes the Murray can flow backwards. I'm not certain as to the mechanism down here.
Just trying to understand, I guess your explanation seems to imply that the Waikul will rise first and block the entrance, and then the Murray will back up onto that.
Yeah. Move on
to the next set of questions. So with the models that you used in the assessment of depth and so forth, and the models that were then used to inform the ecological assessments, were they all just still based on the old Jacobs Burra model?
Yeah, although we did, we tried to align the, I guess, the best Jacobs Burra model that represented depth with the relevant Waikul threshold, so that we could provide, at least to for the ecological benefits assessment, an equivalent depth. Noting that for a pumped inundation event, it is pumped to a target level, and so that target level is kind of, if you're pumping from dry and you've got a low river level, then the level is the level that you get, and the depth is the depth that you get. And so I'm not sure how they've used that information, but they've got a depth of inundation with depth slices. An event, and for a flow, I guess, equivalent to the what would be now the Waikul threshold, but based off the Jacobs model for an equivalent depth, equivalent to the 58.7 meters of target inundation. I probably have explained that really poorly, but we tried to get them depth files that we thought were representative.
And so is that a representative extent of inundation as well? Is it biased towards depth or biased towards extent?
I think it's probably, it may underestimate depth at the very downstream end because of the backwater effect.
Okay, yeah.
I don't know how I don't know how they used the depth data to correspond with the EVC areas, and if they sort of, for an unregulated event, masked out the areas that are outside the managed inundation extent.
It would be helpful to understand what actual scenario information, what they got in terms of if it's over the Jacobs model, presumably it's a Swan Hill flow, at what Swan Hill flow that they had it, and if we could see a map or something of that at that flow level of the depths that they're working from, so that we can, I guess, in terms of interpreting what they tell us and evaluating what they've done, look at what information they had about regarding depth as compared to what maybe the RRC model shows, which appears to be more, I guess, accurate, reflect what's actually happening.
Yeah, I can. I'll check what we provided them with, how they used it. They'll need to, I guess, answer that question. Yeah,
and I will ask them those questions. And the same as the information provided to the people doing the overall assessment improvement in biodiversity too. If we can understand what you've provided to them, then we can ask them about how they've used it and what importance they've put on it. So I guess to find out how sensitive their assessments are to any of these, what I call effects and differences in depth. If they've just looked at sort of wetted area, it may not be sensitive to any of this, whereas if they've really looked at details of very detailed depth information, then it may be sensitive. So with the decision to use the Burra Creek model, is there a reason you couldn't use the RRC model to provide that information?
Well, I guess there's the RRC model doesn't have, as I understand it, certainly doesn't have the VMFRP proposed infrastructure in it. The RRC model is at a broader sort of landscape scale than the Burra model, and also, I guess, to be honest, just in terms of timing and what we could do in the time that was available and the like, there's some of the considerations that the hydraulic model has kind of considered. That's not to say that that model perhaps couldn't be used if it was necessary, and I'm not I guess I'm not opposed to new modeling. I just I suppose our thinking around this is the extent to which it would identify threats or effects that we haven't already kind of considered and included with appropriate EDS. So it's around, we feel that the effects that we've identified are the ones that are the relevant ones, and that there are EDS to enable them to be managed. Not opposed to additional modelling, but I'm not sure how much more information, perhaps other than some additional confidence, it would provide. But
and so you'd be comfortable by the sound by having an EDS requiring some more modelling to, yes, take the best out of the Burra and the RRC models.
Well, I think not opposed to that. The ministers in the EES central assessments kind of requested similar as well, and if that's enables the incorporation of sort of more or specific design elements, then I'm from a technical perspective and a project, can't talk from a project perspective, from a technical perspective, then I'm not opposed to that.
Yeah, okay, thank you. Now I wanted to look at some figures from the was it addendum or annex you provided with your expert witness statement? There are some figures in there.
Yep.
And I was looking at PDF page 3, which is from the Borough model, and PDF page 4, which is from the RRC model.
Sorry, are these in the witness statement or the?
No, there was an annex to it, or an appendix to the witness statement.
I've got them open on my screen. If
Oh, okay. I don't have the appendix open.
Okay,
Perhaps you could, yeah.
Mr. Forrester, that would be helpful. So, particularly interested if we look at, first of all, if we look at the PDF page 3, we look at the plot. I think it's the one in the middle, which is Borough Creek 30,000 megalitres a day existing conditions peak flood depth, and looking at the northern end of the Borough North water management area, and just sort of just trying to memorise what's there, but then flipping across to the next page, which is the RRC model. And there's two runs, one at 24,000, one at 26,000, and the extent of inundation and those at that northern end is quite different and quite more extensive.
I'm wondering if I think that's possibly a typographical error to my embarrassment. I think that 26 should be 56.
Okay.
Oh, hang on. Sorry, no, that'll be
Swan Hill.
no, that's 26 at Swan Hill, 56 at downstream of Walkhall. So this is I guess where the downstream of Walkhall backwater effect takes over and supersedes the Swan Hill effect.
That's right. And so I think somewhere in one of the reports, a comment was made that the depths across the majority floodplain in the two models are similar, but they're at that end, they're clearly not. Between the two models, quite a significant difference there.
So that's the 56 downstream of Walkhall is more similar to the 30 to 35,000 megalitre a day depths and extents as modelled with the original Borough model.
Right. So just in light of that, I'm just going back then to the box plots that you've provided, which provide comparisons of existing and proposed conditions. And as I understand it, based on the Borough model, and based on the 30,000 scenario, the Borough model. I'm just wondering what to make of those, given the discrepancy in even in the extent of inundation between the Borough model and the RRC model. How we can interpret that.
Yes, I think we've said that that the depths are likely to be deeper in reality when you consider the backwater effect. So in that sense, while we've provided the comparison, we've made a note or that the depths are likely to be deeper in the downstream extent.
Yeah. Okay. And in terms of how the box plots for the Borough model account for that, as I understand it from a technical note or some information you provided in the NIA and VMFRP hearing, the box plots only count the cells that are wet, they don't count the cells that are dry.
That's right, they're only the cells that are wet. Yeah.
Okay, so they're just comparing the wet cells, so they're not accounting for the dry cells in there.
No.
So it makes it interesting to make those comparisons. So I guess it's something to be aware of when interpreting that. Okay, now I just want to go across and go through some of the box plots and onto slide 10 in your presentation.
Mm-hmm.
Okay, and I want to just focus on the box plot here, and it shows increases in both depth and velocity in the Borough North water management area. I'm just trying to understand why there's increases in both. Does that mean there's more water?
My understanding from the model is that with the modification to some block banks and the operation of a structure on bank 5, that more water can move in and out, or move in, and that is a factor in contributing to that difference. Okay, so it's just more water. With the two scenarios you've got here, we've got the existing condition and we've got with the regulators open. Did you produce similar data for a situation with the regulators closed, say during a pumped event, and also then with the regulators being opened after an event, as you did for the Naira and Vinifera? Yes, I presented I haven't got them with the regulators closed. Yeah. Because with the regulators closed, there's no movement, so there's no velocity. But we did the effects of a release, and that was, we did it for the maximum inundation for a pumped event with release through the regulators once they're opened. We've not specifically done it for a seasonal fresh when you open the regulators. Yeah. But it would not be dissimilar, and in all probability, the effect would be less when you're only dealing with water in the channel. You don't have the added height of water on the floodplain. The head differential would be lower if you're only dealing with the seasonal fresh rather than the maximum inundation extent during the release phase. So the release phase risk, I guess, if you like, is the greatest risk is represented by the maximum inundation release. Yeah. Okay. And in terms of, I guess one of the reasons we're interested in what happens in terms of depth, in terms of a pumped event with all the regulators closed, is a question of afflux because of the change in water surface slope as a result of the event being filled up and I guess kept at a flat sort of water surface slope as opposed to a slopey one. So afflux in the context of if there was then another flow down the river, or
or just in terms of the water level being higher in certain parts of the floodplain than it would naturally be as a result of the regulators holding it up there.
So we have in the modelling reports, Reconnecting Rivers model notwithstanding, there's tables of afflux levels under those various scenarios. I would have to go through and pull those out if there was particular locations that were of concern, but my recollection is that that there's little difference across the floodplain because the area is so flat that those afflux differences are not that great.
Yeah, I went and looked through the table. I think there was spotted one that was about 1.23 or something, but I wasn't sure if that was due to whether that was actually a site in the creek rather than the floodplain or something like that.
Oh, sorry, a 1.23 metre afflux difference.
Yeah. I'd need to check the tables.
I couldn't comment on that without having a closer look at the tables as well to see what the scenario or the circumstance was around that.
Just to understand whether that was actually in the channel or something like that.
Look, I think off the top of my head, depths of those kinds of magnitudes would typically be in a channel and not on the floodplain. I mean, if we were to look at certainly the pumped inundation depths, the dark blue being greater than 0.8 metres, they're all confined to the creek itself and some of these deeper sort of flood runner sections, whereas the bulk of the floodplain is all in this sort of less than 0.4 and metres deep. So yeah, a 1.8 would be, I imagine, in the creek itself. Yeah.
Okay, and so that pumped inundation, is that the actual depth of water in the pump?
That's the depth of water in the pump when it's pumped to 58.7, the target water level.
Uh-huh. So it's really depths of less than a metre across the flood.
Certainly across the floodplain, yeah.
Yeah, so I'm trying to reconcile that then with the depth information you got of the Borough maximum scenario, where the box plots are showing sort of depths of average depths in the proposed conditions with around about a metre, and with at the outside going up to 2 or 3 metres. So this is on slide 11.
Yep, that's on here now.
Yeah.
So on the floodplain itself, we're in the less than, for the most part, less than half a metre, with the odd outlier in the 1 to 2 metres deep, and then within the creek itself, around the regulators and within Borough Creek itself, that's where you're seeing those deeper depths.
Okay, so
some of those outliers there would be perhaps related to some of these deeper parts within the floodplain itself.
Yeah. Okay, but the first 4 zones on that box plot there, are they all then in stream location?
They're all in stream, yeah.
Okay,
upstream and downstream of B1, downstream of B2, and more generally across Borough Creek itself.
Yeah, and then the floodplain depths.
And then the floodplain, yeah.
Yeah, and so that with the map that you were just sort of flicking to and from, is that out of the Jacobs Borough model?
This,
or is it the RRC model?
No, this is out of the Jacobs model.
Okay. Mm-hmm. Okay, thank you. And with the Jacobs model, what is does the model show anywhere what direction of flow it's assuming when it works out velocity and shear, or the shear stresses?
I would have to take that one on notice.
Yeah, particularly interested again with the I guess with the tailwater base level being different, whether they're assuming that's such a big difference, whether they're assuming outflow rather than inflow.
Yep. I'm assuming it does, but let me get a proper answer on that. Yeah,
it would be good to understand that, and also I guess if they've made different assumption about how the water moves into the floodplain, simply because of that wall-call effect not being there, and therefore not so much water being pushed in at the downstream end. I just got a question while we're still on these box plots of depth about there's a figure 3.9 in the what I've referred to as the addendum report of the supplementary specialist assessments, which compares what it says existing conditions and RRC existing conditions. Does existing conditions, does that mean the Jacobs report?
That's the Jacobs existing conditions compared to the RRC existing conditions.
Okay. That's what I thought, but I didn't want to presume.
Sorry, yeah.
That's okay. Let's move through. Now I wanted to change the subject onto something quite different and talk about Blackwater.
Mm-hmm.
And I guess given the changed understanding of how this floodplain operates as a result of the war-cool effect, just wondering about how that, what implications that has for Blackwater and the presumption of through flow. Because the original presumption of the Jacobs model without that backwater effect is there'd be water moving downstream and out of this floodplain. And looking at the node diagram that's in the appendix to the specialist assessment, it basically does show that it shows water coming into Borough Creek, moving through and coming out through regulator B1, but not coming in through regulator B1. So I'm just wondering what difference this Weichel effect what effect it has on, I guess, your conclusions about Blackwater.
So do you mean during an unregulated event with all of the regulators open, or during a pumped event?
Well,
or
I guess
both.
a pumped event's a pumped, or both, or
Or
a
both.
natural event or a flood capture event.
Yeah, so the unregulated event with all of the regulators open, I guess we're treating that as if the floodplain would respond in the way that it would respond to a natural event in terms of the development of Blackwater, and in the as exhibited assessment, we modelled flood capture and showed that, yeah, there's the risk of Blackwater occurring. The revised assessment, given that when an unregulated event does occur, generally meets the duration of inundation. We haven't specifically modelled a flood capture associated with an unregulated event, because those unregulated events as they currently occur meet the duration. If you were to do a flood capture, then we would expect that there'd be Blackwater effects associated with a flood capture event, because you have captured water and held it on the floodplain. For a pumped inundation event, I think we've demonstrated that if you do pump water onto the floodplain and hold it there, then there is this potential for dissolved oxygen decline to occur, and that a reasonable amount of through flow in that situation is required to mitigate that effect.
So with that through flow, so I guess you mentioned before that through flow, the pumps may not be big enough to provide the required through flow.
Yeah, that's a potential effect. I suppose one thing I'd say in relation to the modelling and observations that we've made, not so much to do with the pumped inundation, but with unregulated events. Even with the unregulated events that do occur, we see variable dissolved oxygen concentrations across the floodplain. So the modelling in that sense is possibly overestimating the severity of a Blackwater event, and that there'd be, in reality, locations and areas of better DO. And even if you were not able to generate that sort of high level of through flow to reoxygenate the whole of the inundated extent, nonetheless, even small volumes of through flow coming in, you would be able to create areas of higher dissolved oxygen at the point of where that through flow enters, and it would persist for an extent. It may not, to get it to kind of apply to the whole area, then you need much larger volumes. So even small volumes of inflow would be beneficial in terms of creating refuges.
And in terms of providing the water for that through flow, would that be something that'd be factored into the sort of order for the water for that water allocation, that X amount of water to inundate the flood flow plus X amount of day to maintain the through flow? And if that could be done, that watering event wouldn't be done.
Well, I would presume so, that would need to be considered, but also that the volume of, if everything's, seepage and evaporation losses aside, there'll be a volume of water coming in and a volume of water going out. And so from a water accounting perspective, there may be ways that the water holders account for those sorts of through flow volumes where, you maybe will apply a loss of a certain percentage, but that a certain volume is recovered at the downstream end as that water spills out at the downstream end. And I mean, I think the water holders take that into consideration, those sorts of passing flows, and also when a release is made following a managed event, some of that water may well be reaccounted for when it comes back into the river.
Let's see. So other question I had about black water is the effect of the containment banks, because currently the movement of water in and out of the floodplain at the downstream end is unrestricted, but we don't really, as you say at the moment, understand quite how that interaction works. I'm wondering if the containment banks are the spillways, whether that might reduce the interaction between the northern end of the Burra North floodplain and the river, and then may have some effects on black water in unmanaged events.
I guess it's possible, subject to that understanding of the effect of the containment banks. I think what we tend to see in these sorts of inundation events is that across sections of the floodplain that you will get black water occurring, and that in the flowing reaches of the Anabranch systems and the like, they tend to have a better quality because they are flowing. So it may not make a difference to the severity of black water that could occur anyway.
If I could just jump in with a follow-up question there. There's the I think it's the B1 regulator is the large regulator at the sort of top of the containment bank. The rest of the containment bank, and correct me if I've recollected this wrongly, is spillways. But was any thought given to whether there would need to be more regulators to allow that flushing or flow through effect if you did end up in a black water situation?
I know for some of the other sites, there are minor regulators along containment banks where there's an obvious flow path from the floodplain to the river. So the spillways are in effect a release mechanism, I guess, and they're in sort of low-lying areas, but they're not on what we would call sort of effluent or floodplain creeks as such. For other projects, there are regulators if there is an actual creek, and so those regulators do allow for movement in and out where there's an obvious creek,
a waterway.
Yeah. So to that extent, if they were, I guess, required, they would have been included. But the main outlet for water shedding off the floodplain is through Burra Creek itself.
Okay. All right, thank you.
Okay, I'll just move across now onto the question of erosion, and across to the question of Murray River bank erosion, which is relevant because some of the containment banks are quite close to the Murray River. In the in specialist assessment C, in Appendix C, which is a borough geomorphology, the geomorphologist actually points out in relation to the access track and the bank erosion to say there are indications that the bank is actively eroding as evident by the exposure of tree roots and lost value material for the bank face. Bank erosion is a risk to project infrastructure. Based on that, did they or you have any input to the siting or micro siting of the containment banks to avoid that erosion risk?
No, they've identified it as a potential issue that needs to be considered as part of containment bank design. And I think within the EDS for detailed design, the containment bank design would need to consider that.
And so you think that's picked up in an EDS?
It's intended that it's picked up in the EDS.
Yeah, it'll be good to understand if it actually is picked up in an EDS or where it is.
Well, the requirement to consider those risks is the intent of the EDS. I guess I'm not involved in detailed design, so I guess there's a step to make sure that happens.
Yeah, I guess there's maybe a question to you, maybe a question to take back, or maybe a question to Mr. Forrester, a question on notice in terms of which EDS does actually pick that up.
To avoid me not wasting time, spending time searching through to find the right one. Can we take that one on notice?
Oh, absolutely.
Yeah,
Yeah. No,
thank
question
you.
on notice. Yeah. And the other thing, which may end up being a question on notice too, but on the maps of shear stress, you show very little shear stress downstream of the B1 regulator. But looking at the Murray River, there's quite high shear stress at certain locations in the Murray River. And particularly, there's a couple of locations where the containment bank's close to the Murray River bank, where the shear stress in the river is also high. I guess I had a similar question there about whether you thought that had implications for the siting of the containment banks, and also how that's has or should be dealt with in the project design, or up to date, or the detailed design.
Well, I think that let's take that one on notice as well, in terms of, because it's related to the EDS and what they would do at detailed design, what information they might need to consider those effects.
And what would you expect them to do at detailed design if they were considering effects? How would you expect them to respond?
Well, the containment banks are relatively low embankments, and so it might depend on what height of bank is proposed at particular locations as to whether there is a particular risk or not. And so I imagine that they would need to take that into consideration, and the distance between the river and the containment bank itself. The containment banks, as I understand it, are proposed to be, for the most part, put on tracks, existing tracks. So I guess that means there's not just proposed infrastructure or assets that are at risk of bank erosion, there's existing assets, tracks and the like. So that would be, I imagine, part of the consideration that they would undertake or take on board when they're looking at the design for those banks, the specific design.
And so would you then expect them to, if they identified an area of being significant risk where the bank or erosion of the riverbanks may threaten the project infrastructure within the life of the project, would you expect them then to put stabilisation structures on the riverbank, or to move the containment banks further away from the river?
That would be presumably a site-by-site consideration as to, what's feasible at the particular site and what could be done, either to help, I guess, mitigate the effect on the riverbank itself, if there was something that was able to be done there, or if there was an obvious alternative to the location of the containment bank. I couldn't speculate that it'd be a site-by-site kind of assessment.
Do you agree that in principle that it would be preferable to site the banks in an area, the containment banks in an area where they weren't going to be at risk of erosion during the life of the project?
Well, I think, obviously it would, you don't want to put anything where it's ultimately at risk. But again, it's a site-by-site consideration as to whether the risk is real and evident. And my understanding is that that would be dealt with through the detailed design process. Yeah.
So in terms of the detailed design, who would you, what kind of person, what kind of expert advice would you expect to go into that process? Would it be design engineers? Would it be geomorphologist advice? Or modelling? Yeah. And so that presumably would need to be specified in the relevant EDS to say who or what considerations need to be put in there.
If you were wanting to make the EDS as explicit as possible, then yes, you could do that.
I'm looking through my questions. They're all my specific questions, Member Carlisle. Also notice we have that list of general questions, but I've sort of...
Our general questions have been somewhat overtaken by the specifics. I'm just going through my list here. I think I got a couple of questions left. My questions are going to be a little bit higher level because I'm a lawyer, not a technical person. So I understand with these updated project scenarios, we're upping the number of pumped inundation events in a year compared to what was originally exhibited. I think we're looking for 3 more managed inundation events in over a 10-year period.
10 years, yes, yeah.
Yes. I don't want to get into too much detail about this because the committee's already found that water allocation issues are outside its scope, but I understand you've assumed that there will be enough water available for the VMFRP projects. Is that right?
Yeah, well, I've been advised that there's enough water available. So, yeah.
And I'm just trying to, I'm not really questioning whether or not there will be. I'm just looking at the scenario, no matter how hypothetical it might be, that if there wasn't enough water available for these additional pumped events that you're now proposing, would the assessment of impacts of the project be as originally assessed in the exhibited ER rather than the updated assessments in light of the the war-cool effect and the updated specialist assessments?
What we've done is assess the effects related to the proposed infrastructure and the way they'd be operated. I guess in terms of there's a number of different sort of elements though to these projects, and the frequency of inundation and the duration of inundation, whether a pumped event is needed or not in any one year, it is informed by the need or the needs of the vegetation communities that are present on the floodplain and the like. So in terms of the assessment of effects, whether water is available or not hasn't really factored into our assessment of what happens if you deliver a pumped event.
Okay.
It's kind of, I guess, it's not theoretical. We've looked at what happens if you deliver a pumped event, or what happens if an unregulated event occurs. What are the implications from a water quality perspective and an erosion risk perspective and the like?
Yep.
Whether an event gets delivered or not is an operational decision based on the condition of the vegetation, the time since a previous event occurred. So let's, for argument's sake, that we've had 2 unregulated inundations in a year, in 2 years now. The vegetation might take on a really good response, and monitoring demonstrates that it's responded well to those unregulated inundation events. And the coming year looks like it's going to be a dry year, but a decision is made that, well, we're unlikely to get an unregulated event because we're heading into dry conditions, but the vegetation would really benefit from a 3rd year of inundation to really build on the good outcomes that we got from the last 2 unregulated events. And so under that circumstance, a decision might be made to deliver a pumped event subject to there being water available, sort of thing. And so that would be the process I imagine gets followed.
Yeah. Okay.
So we've assessed what would happen if you deliver a pumped event. The decision to deliver a pumped event, either a once-off or for 3 years in a row, required that is operational decisions that would be, I guess, developed up by the CMA and the water holders at the time. Okay. I don't know, does that sort of help answer the kind of sequencing?
I think what you're saying is you've assessed the impacts of a pumped event. You haven't assessed the impacts of not doing a pumped event.
Well, that's right. I mean, the impacts of not doing the event are, when it might be needed, are that the vegetation continues to deteriorate. And that, I guess that's a question for the ecologists, the floodplain ecologists, when they give their evidence, would be to say, well, what if we don't do anything? The river's flooding now. Everything looks all nice and good. So what if we don't do anything? And they would be able to answer that question. Yeah.
Okay. Just a question about this containment bank. We've sort of talked about that a bit already, but the containment bank is going to be built. There's a couple of block banks that are going to be removed. What's the sort of net effect of all of that in terms of the movement of water in and out of the floodplain? I'm sure it's in there somewhere. I'm just not quite sure where in the assessment it's been addressed, and whether there is any implications on the original assessment based on the wall cool effect, I should say.
Yeah, well, I mean, I guess that sort of question relates to the sorts of questions that Member Briscoe was asking around the location of containment banks and whether are they kind of given this understanding of the walk wall, whether they're still in the right spots.
Yeah.
The containment banks and the location of regulators would have been originally identified as, well, the containment banks as locations where there were potentially low spots that the use of a containment bank would help to, as the word implies, contain water within a ponded area during a managed inundation event. So there's,
well, I guess it was
obviously some sort of effect during that situation, but they're not sort of massively high levies and the like. They're designed to be overtopped, and so that water can continue to move around the floodplain. And they're typically at the highest points anyway, except that if there's a little bit of a low point between two high points, they sort of fill in that gap, I guess. And so they're at the very margins of, for the most part, the inundation extent anyway.
Yeah.
Subject to Member Briscoe's kind of questioning around the effects of the backwaters. In terms of block banks, there's certainly one block bank that would be removed, and that would help with the better connectivity of water up and down Burra Creek. There's an existing block bank 5, that I understand has a pipe in it, and that pipe would be operated and would effectively recreate the connection in a more meaningful way than is currently occurring. B1 regulator itself is at an old location of some sort of form of impediment or embankment, or not embankment, blockage in the creek anyway. And so in that context, all of those things are good for improving connectivity across the floodplain and within those floodplain creeks. And to the extent that you can remove block banks, that's a good thing, because anything that improves connectivity is of benefit. That's not to say they don't result in a change in condition. And if you've got block banks in place that are sort of preventing flow from getting from one part of the system to the other, then you've got ponding, and we've seen that at Nyah and Vinifera. There's certainly at Nyah, there are block banks that are preventing flow down the creek, and the removal of those block banks opens up the creeks, allows flow to pass down the creeks. It does change velocities and depths and the like, but in a good way, because we're now creating through flow, we're creating passage for fish and the like. So there's benefits of those block bank removals where you can, it'll result in change conditions, just like in a more frequent inundation, it has the potential to result in a change in vegetation type. But I mean, that's kind of an objective for the projects, is to perhaps reduce the extent of terrestrialisation in certain parts of the floodplain. But I mean, the ecologists will talk to that.
I guess perhaps this is something to put Mr. Forrester on notice about, that we would like addressed in closing submissions. It's just, look, we are a little bit troubled, as you can probably tell from the questions that have been put to date, about that containment bank and its effectiveness in achieving the sort of project objectives, or possibly impeding what we now understand to be natural processes that weren't understood when the containment bank was designed. The containment bank seems to be, or the location of it seems to be, influenced by the location of the, existing access track and by low points, as Dr. Treadwell just explained. But whether that whether there needs to be another look at the design of the containment bank in light of the war-cool effect and the way that water is moving in and out of the floodplain. So we might just get you to address us on that in closing. I just want to ask another fairly high level question about the black water events, and the main mitigation strategy for managing black water events seems to be allowing some sort of flow through. You mentioned that you need pretty high rates. I think it's 100 megalitres a day to get, you know, an appreciable effect. The effect at lower flow through rates is less beneficial. But how in an operational scenario, practically, do you balance the need to contain water on the floodplain, which is the whole point of the project, and allow flow through to maintain that water quality?
So in an operational sense, you set the level of the downstream regulator at the height that you want the water contained at, and you can then allow inflow at the top end or from the, and that will spill over the regulator at the downstream end. And so in that context, you maintain that area of inundation because it's set by the level that you've set the regulator at. And in this instance, it's 58.7 metres AHD. It just means that if you're able to provide through flow, then a portion of the water that comes in at the top end or wherever it comes in at will go out at the bottom end. So
you just need to pump more water in. Let's use the top end and the bottom end.
Yeah,
because water
simplifies it. Yeah.
But you pump more water in at the top end.
Yep.
To detain the amount of water you want to detain in the middle, and the overspill flows through at the bottom end.
Yeah.
Okay.
And I mean, again, getting back to the mitigation of blackwater effects, even small volumes at a quite local scale would create refuge. They may not extend into the full extent of the floodplain, but even during a natural event, we see similar kind of outcomes where you've got parts of the floodplain that can experience quite low dissolved oxygen and other parts of the floodplain that continue to exhibit reasonable oxygen, and they're sort of areas of refuge for fauna, that fish and what have you, that might need to find that
that's
refuge.
Something I think we can explore with Mr. Benier on Monday. Again, we're sort of getting back to a fairly basic question from a lawyer rather than a technical person, but I'm just getting my head around the erosion risk. So the erosion risk is from the project, and I'm not talking about the river itself, where, as Member Brisger mentioned, some of the shear stresses are quite high. But the erosion risk as a result of project infrastructure is primarily downstream of the regulators. Is that right?
That's right. They're the locations where there's potential for higher velocities.
Yes.
And that represents, I guess, the potential for erosion. But even though you have a higher velocity under certain circumstances, doesn't necessarily mean you'll experience high erosion.
Yes, sure.
There's a whole bunch of kind of factors that relate to that, and the measure that we've used as a measure of erosion risk is bed shear stress.
Yes.
And it's I guess a measurement of force. And so we've identified, geomorphologists have identified criteria that represent different levels of erosion risk, and those bed shear stress criteria or thresholds are related to the type of soil present in those locations, whether they're vegetated or not. Certain soils are more prone to erosion, and so they will erode at a lower bed shear stress. Yeah. So the thresholds have been identified based on the characteristics of the system, and in fact they've been varied across all of the VMFRP project areas to the extent that it's necessary to account for different soil types and different levels of vegetation.
Mhm.
And so even though there's an increase in velocity potentially under certain circumstances, depending on how you operate the regulators, it doesn't translate to a particularly significant increase in shear stress. And so in that context, we think the erosion risk is manageable, or it's low, and it is further manageable through the operation of the regulator so that you don't release large volumes of water really, really quickly all of a sudden. You do it in a staged way.
But both velocity and bed shear stress have been assessed across the whole floodplain. It's not limited to just around the.
No, we've looked. It's been
regulators?
looked at across the whole floodplain and around the regulators, but the spot that represents the highest level of risk is around and downstream of those regulators.
And I suppose the drop structure, and the whole point of the drop structure is to control that erosion risk
That's
as
right.
water is released back.
And that drop structure at the moment, there's already erosion, as I understand it, occurring at that location. And so there's already across the floodplain areas of erosion and areas of deposition. It's a natural process. I mean, we could argue about the extent to which it's changed as a result of river regulation and things like that, but the formation of floodplain creeks and the floodplains themselves are all a function of erosion that's occurring kind of all the time. And so what we're, I guess, saying is that we don't think the effect is significant in the context of all of the other things that are going on, and it's manageable through appropriate operations.
And does the walk-haul effect, and the walk-haul effect isn't present in all the operating scenarios.
That's right.
So I get that. But does the walk-haul effect overall, what impact does that have on the erosion risk presented by the project? Does that alter the risk profile that was previously assessed?
Well, I think it probably reduces the effect to some extent during an unregulated event if you've got a higher downstream water level.
And is that presumably because that will slow the velocity?
Slows the flow down, slows
Yeah.
the velocity down. Yeah.
Yeah.
So if you were making releases from the floodplain when you've got a low Murray River water level, then you've got what they call a higher gradient, and that water will flow faster and there's more opportunity for it to cause erosion. But if the downstream water level's high, then it's coming out much more slowly, and so the erosion risk is less.
Okay. Though that was it from me, I'm just going to go. I can't see Dr. Kelly on the line. Are you on the line, Dr. Kelly? If you are, could you just turn your camera on? Okay. Either Dr. Kelly is not with us or doesn't have any questions for you, Dr. Treadwell. I think that brings us to an end for things that we need to discuss today. But because we had quite a long list of questions on notice, some of which I got and some of which I'm going to need Member Briscoe to clarify. But I thought we could just spend a moment going through those. There was only one for Mr. Hoxley, so that's easy. We'll start with that one. And that was just to check what those existing bores are actually monitoring, whether they're monitoring shallow aquifers or deeper aquifers. I think that was essentially the question to Mr. Hoxley. And I'm sure Member Briscoe is going to jump in if I get any of these wrong. On your list, Dr. Treadwell, I had stats on the Burra intermediate scenario happening without intervention.
Yep.
I had the resolution of the Burra model versus the reconnecting river country model.
Yep, we've got specifics, the various modelling kind of parameterizations and specifics. Yep. I've
noted down, I think in very broad terms, the issue. I'm hoping the detail down there. Output files for the RRC model on depth, velocity and shear stress.
Yep.
Yeah, we don't actually need the output files. We just need
Just want to know
roll.
what it was.
What
Yep.
happened to those output files? Yep. Let me just. Whether the RRC model is a steady state model like the Borough model,
Yep.
or whether it's a variable flow rate model.
So there is a table in Appendix B or C of the attachment to addendum that lists the differences between the two models. So I don't know whether that provides all of the kind of information around the modelling formats and resolutions and the like, but we can re-provide that table so that as part of a response and include including that response what exactly did RRC provide to us in terms of model output, so we can package up a response. But yeah, just point out that there is that kind of comparison in the addendum documentation already.
Yeah, I've got that.
That would be useful. Sorry, you go, Member Rita.
Yeah, I was going to say I've got that in front of me. So I guess if you could just add some information on the addendum addressing some of the specific questions we had in terms of, I don't think it's clear as to whether it's being run for flood events or it's just being run to steady state at particular flow level.
Yep.
And so
I'll double check all that.
Yeah.
Yep.
I think if we could get a technical note that just packages up the answer to all these questions about the Borough model and the RCC model RRC model in one place. And if you need to cross-refer to parts of existing documents, we're more than happy with that. But just so we've got one reference point to understand the modelling would be really helpful. The next one on my list, I've got, there's a bit of background noise coming through there. Okay, that seems to have stopped. The next one I've got question mark, where breakouts occur at higher flow levels. So I think I'm going to need Member Brisger to translate that one.
Okay, I'm just trying to think where, because I was paying attention to Dr. Treadwell's answers and I wasn't paying attention to writing down detail.
That's why I was trying to write down the answers. If it helps, it was in the, we were discussing the, I think it's figure on slide 5 with the big red triangle in the middle, red rectangle in the middle, and the flow rates of the Murray and the flow rates from the Wakul.
This figure 3.7 was the...
Yes.
I've got that one on my list. I've even drawn myself a little diagram so I understood the question.
Okay, good. Next on that I've got on the list is Sentinel elevation resolution on figure 3.4, which it sounds like you've got on your list as well.
Yep.
Accuracy of surface levels as inputs into the modelling to predict when inundation will occur. That's that sort of, I guess we didn't actually use the term sensitivity analysis, but just understanding if you got the surface levels out, what would that mean for when we can expect inundation to occur?
Yeah. Yep.
Information on whether the Jacobs model can assess the impact of the wall-cool effect without the containment bank in place. So that was that question about, could you rerun the model without the containment bank there and see what would happen? I'm not sure if I recorded that entirely in enough detail.
Yeah, I think
it was to get an understanding of the whether the containment bank is going to impact on what would naturally occur when you've got high flows out the Wall-Cool junction and you get.
I understand. I've got a note to the extent that does the backwater effect change where containment banks are located or have an influence on the way the water interacts with those
Yes.
compared to what was originally modelled. Yep.
Exactly. So that's because obviously the RRC model didn't assume the existence of the containment.
No, it doesn't.
And, yep. Okay. So it sounds like you've got that one. Assumptions about the direction of water movement in the velocity and shear stress calculations.
Yep. Got that.
The EDS that picks up the erosion effects.
Yes.
And the last one on the list is whether the containment bank design has taken shear stress in the adjacent Murray River into account.
Yep.
Was there anything I missed there, Member Briscoe?
I think in that Dr. Treadwell mentioned that there may be an EDS already addressing that or pointing to a requirement for those things to be addressed in detailed design. So if you could point us to that, if that EDS is there, and any specific recommendations that it has in terms of what might be done to resolve those issues too in the design.
Okay.
And I guess with the containment bank question is really maybe making the question a little bit more general in terms of what insight can be shed into how the flows behave in the vicinity of the containment bank based on whatever modelling is available currently and what other information, site information is there to understand sort of what the current hydraulics are and then therefore what effect the containment bank will have on those hydraulics in light of that lock-cool effect.
Okay. I mean, we're anticipating that those matters can be dealt with in writing, but if there was any further questions that we needed to ask of you, Dr. Treadwell, about that material, is there any availability constraints over the rest of the roundtable that we should be aware of? Like, I'm just wondering if we needed to slot you in for a schedule, you know, for a short return appearance, so to speak, when we might do that.
There's nothing specific. I generally don't work Fridays, but if it's I can accommodate that. I don't know what the dates are, but I've not got any leave or other things booked that preclude me from being available at some point if it was requested.
All right, that's good to know. Is there anything else that anyone wanted to raise before we close for today?
I've just had one other point of information that we were interested from Dr. Treadwell, and that is to understand what information was provided to the other experts, particularly the vegetation experts and the team doing the overall assessment of improvement of biodiversity as to what hydraulic information they were given.
Yeah, and I think that was particularly in relation to depths. There was some discussion around depths.
Yep, I've got that one on my list too.
Yeah.
Member Carlisle, if I might just ask a couple of questions while Dr. Treadwell's here, and in relation to one, really a matter of clarification in terms of a couple of figures that were looked at and compared.
Sure.
It's really in relation to the discussion, Dr. Treadwell, of the specific flow levels or flow thresholds and their relationship with particular extents of inundation. And the references made throughout various documents to, for example, the former 30,000 megalitres a day at Swan Hill and peak flood depths shown in your document B13A, the annexure to your witness statement. I'll just share the page that we looked at. Here we are. So as I read these figures, when they refer to this flow level at 30,000 megalitres a day, is it the case that those sorts of flow levels have a direct and unchanging or invariable relationship with how inundation spreads across the floodplain, such that we could say, today if there's 20,000 megalitres of flow downstream of at Swan Hill, we know exactly what inundation will be at the floodplain?
I'm not quite sure I follow the question. Those maps as presented there and don't include the backwater effect from the Walkle River. So they're the that's the inundation extents that you could expect if the only source of flow was the Murray River at Swan Hill.
Yeah, and is it also the case, I was just looking at this Annexure B or Appendix B to the updated specialist assessments. As I understand it, the models which have produced those figures or led to those figures being produced also assume inflows using historical flows taken from big mod outputs, for example, such that they're having regard to, well, they're produced in the context of this 30,000 megalitre a day flow, but I presume on that basis they also include or are based on inputs, assumptions regarding how long that flow occurs for and perhaps how wet the catchment might otherwise be, in the sense that they are situated in the context of a historical catchment condition. Is that right?
Yeah, insofar as that big mod flow outputs and the Swan Hill gauge and the like were used more for once it had been, I guess, originally determined or confirmed what the then thought inundation threshold was, then those historical flows were used to help inform the frequency of inundation and the duration of inundation above the thresholds that the modelling had predetermined.
Yeah, and insofar as they represented or they used the big mod outputs and so on, they represent, I'm sorry, my controls are in front of my document here. They represent this sort of typical condition for a 30,000 megalitre a day flow. We looked and compared that with the RRC modelling existing conditions, inundation extents, on the next page of B13A. And we were looking at the comparison between what's shown for the, I'll just refer to the downstream Warkle junction, 48,000 megalitres a day and 56,000 megalitre a day images here, and the comparatively larger extent of blue, of the light blue and the dark blue. As I read this legend, it refers to the dark blue as the more typical inundation extent for flow option and the lighter blue as the upper limit of inundation extent for flow option.
Yep.
When you say at page 3 here that the inundation extent for this 30,000 megalitre a day Jacobs modelled inundation is equivalent to the RRC modelling for this flow downstream of 56,000 megalitres a day. On my comparison of this light blue shown for the Jacobs modelling and the reconnecting river country model, that seems to be a statement which lines up with the darker blue. Is that right?
That's right. Yeah. So the way I understand the reconnecting river country modelling was that they've kind of identified a bit of an envelope of inundation that might be, that they've modelled could occur for that flow threshold, and presumably some of their model runs had perhaps a larger inundation extent than others. But what they've mapped here is that the typical inundation extent that they would expect is the dark blue. There may be some circumstances where you get inundation equivalent to the light blue based on the model runs that they've run, but the dark blue there in the 56,000 most closely matches in terms of inundation extent the 30 to 35,000 Jacobs model run.
For that one scenario of the Jacobs.
Yeah. Yeah.
Okay. So presumably the upper limit of inundation extent shown in the RRC modelling figures here would be reflective of, a longer duration of these flows or a wetter catchment or both.
Possibly, yeah. Yeah, all absolutely things like that. There may be, in reality, slight differences in timing between the Walkle flow and flow coming down from Swan Hill and those sorts of interactions. I guess there's lots of reasons why in reality a flood of a particular level is slightly different to the same level that flood got to on a previous occasion.
Yeah, okay. Thank you, Dr. Treba. Thanks, Member Carlisle. That was all I had to add.
Okay. Anything else anyone wanted to say before we close for today?
Yeah, I wouldn't mind saying something or asking a question.
Is that you, Dr. Kelly? Because we can't see you.
No, I've had to come in the car somewhere, so I'm not sure if you really want to see my internal of my car.
Oh.
I'll put it on if you like. There you go.
Okay. What was it you wanted to say?
Oh, I want to ask a question. And sorry before about that noise.
Oh, no, that's okay.
Can you hear me okay?
Yep.
So, Mr. Treadwell, thank you for your presentation. And the Connecting River Country model, is that, I'm just wondering, that's New South Wales, isn't it?
Well, New South Wales and the NDBA built that model, but it covers Victoria as well.
And when did that become available?
Towards the end of last year, early this year, was when it was more publicly available. It's very recent. It's very recent.
Yeah, and they did stuff to do with Victoria as well.
Well, they've modelled, I guess, the whole of the floodplain at a agnostic of states.
How lovely is that? Yep. So you said something about unregulated flows, it won't be substantially impacted in your presentation. I'm not sure what you meant by that. I didn't write enough notes to know what my question means, so I might just skip over that. Have you got a graph of the War-Cool flows?
Yeah.
So is that in any of the documents or your presentation?
Yeah. In a graph in what sense though? Because there's lots of different graphs. I've got a time series of flow in the War-Cool, and of flow in the Swan Hill at the same time, and it goes back for, I don't know, 40 odd years, showing the time series of the different floods as they've come down the river, and you can compare the War-Cool, the downstream. Oh, sorry. Let me correct myself there. I've got a graph of flow in the Murray River downstream of War-Cool. I haven't included a graph of flow just in the War-Cool, just to make that distinction.
Yeah, okay.
To be clear there, what impacts the Burra Creek floodplain is the flow at the War-Cool Junction in the Murray River, not the flows upstream in the War-Cool River. What we need to know is what the flow rates are at the War-Cool Junction.
Yeah, I'm aware of that. So the other one was, is the Murrumbidgee involved at all, like the Murrumbidgee Junction and the pushback that causes when there's a high flow in the Murrumbidgee? Yeah,
we don't believe so. That's even further downstream, and that the effect is it's driven by the War-Cool, which is the closest.
Just the War-Cool runs very low a lot. So the other one was, you said something about on one of the graphs that the flow at Swan Hill hardly ever gets above 25,000, right. Or is that because of a thing called the Turrumbry rule? Because of regulation, they don't let it get higher than that.
There's a combination of reasons, and that may well be one of them. The Murray through that section of the country is very narrow, and it breaks out upstream and heads out over country through the Edward system and through the breakouts along the northern bank through Gumbower and places like that. So there's a capacity, I guess, constraint. Sounds like an awful word. There's the river is confined and constrained in terms of how much flow it can carry through that area, and so that's one of the reasons why you get these breakout flows occurring during big flood events, and the river doesn't get much higher than the 25. On occasions it's got to 30. Now, yeah.
I suppose when you're talking about the effects of the Walcool and high flows, you can just see that around there everything's very connected and interconnected in a more complex way than we really know. So yeah, just having a look if I've got any further questions. It doesn't look like I have. Yes, that's about it, I think.
Okay.
Oh, one thing, sorry, last one. With adaptive management, my concern is, I suppose, just to background it, you build these large infrastructure projects, but then there's no money left and everyone walks away and there's not enough staff to manage it properly. So how can we be assured, and do you feel confident that there'll be enough staff located locally to manage these infrastructure in such a way that we get it right with the proposed watering scheme and opening and closing, etc., etc.?
I think that's probably more a question for Mr. Forrester. It's a question that the proponent probably needs to answer. But Dr. Treadwell, if you've got any thoughts about that, we're happy to hear from you.
Well, I think with all of these types of, I mean, let's be honest, they're interventions. They need to be monitored and they need to be adaptively managed. And you learn by the past operations and you use that to inform ongoing and future operations. And so from a management perspective, the operation of these need to be informed by adaptive management. And I'd like to hope that the appropriate sort of funding and commitment is provided to enable that to occur. I can't comment any further than that, other than to say, yeah, adaptive management needs to happen as part of the operation of these types of projects.
Yep. And just sorry, there was one last one. With algal blooms, and you talk about adaptive management and monitoring, why can't we, and this might seem stupid, but why can't we manage to prevent algal blooms? And why can't we, with all the ways we have to intervene and control things and knowledge we have, why can't we prevent them?
So are you talking about sort of algal blooms in general along the whole of the river, or algal blooms just? I think anywhere. Yeah.
Well, in the project area.
So in the project area, there are things that that you can do around the timing of delivery of water to avoid periods of the year when algal growth is more likely to occur. That's not to say that algae doesn't grow in winter. It's just not as kind of rapid growth. And there'll be algal growth occur. That's part of what happens when you inundate a floodplain and when you have water standing around. Even after the flood's receded, there'll be parts of the floodplain at Burra, at other sites, that will retain water for a period of time, and algae will grow in those ponds or those wetlands, and eventually those wetlands will dry out. That's a natural kind of process of wetting and drying that occurs on floodplains and occurs in wetlands, and it results in severe water quality decline as those systems dry out. But that's part of the process, and it's a natural kind of occurrence. It's just what happens. And if you're a fish that happen to be trapped in there for whatever reason, then you'll die. And this happens irrespective of the way that you might manage or have a managed event or a natural event. Algal blooms in the Murray are a really contested kind of issue, and they're a result of a whole bunch of things around river regulation and farm management and all of the sort of, let's be honest, the travesties that have been applied to that river over time. So when things are like algal blooms are a consequence of the way the river's been managed over a long period of time, it takes a lot to unpack and work out how do you reverse all of that, or how do you manage that. And yeah, there are things that they try and do by releasing water at certain times and improving farm management and reducing nutrient runoff from farms and trying to clean up irrigation drainage, and all those sorts of things are aimed at trying to reduce the nutrient inputs to the river and try and, to the best extent, manage algal blooms.
Yeah, thank you. I just hope that, with all this knowledge and research and management that we're going to do, that, I know sometimes these things happen in nature. I don't think they happened as much years ago, but that we can maybe manage to stop algal blooms too. Thanks very much, and thank you, Member Carlisle.
Okay. Third call for final issues to raise before we close for today. Okay, well, I've just got one more thing to say before we close, and that is go Matildas.
Yeah.
We'll see you all on Monday. Thanks, everyone.
Thank you.